All right, welcome back, everyone, to an introduction to artificial intelligence with Python. And last time we took a look at how it is that AI inside of our computers can represent knowledge. We represented that knowledge in the form of logical sentences in a variety of different logical languages. And the idea was we wanted our AI to be able to represent knowledge or information and somehow use those pieces of information to be able to derive new pieces of information via inference, to be able to take some information and deduce some additional conclusions based on the information that it already knew for sure. But in reality, when we think about computers and when we think about AI, very rarely are our machines going to be able to know things for sure. Oftentimes, there's going to be some amount of uncertainty in the information that our AIs or our computers are dealing with, where it might believe something with some probability, as we'll soon discuss what probability is all about and what it means, but not entirely for certain. And we want to use the information that it has some knowledge about, even if it doesn't have perfect knowledge, to still be able to make inferences, still be able to draw conclusions. So you might imagine, for example, in the context of a robot that has some sensors and is exploring some environment, it might not know exactly where it is or exactly what's around it, but it does have access to some data that can allow it to draw inferences with some probability. There's some likelihood that one thing is true or another. Or you can imagine in contexts where there is a little bit more randomness and uncertainty, something like predicting the weather, where you might not be able to know for sure what tomorrow's weather is with 100% certainty, but you can probably infer with some probability what tomorrow's weather is going to be based on maybe today's weather and yesterday's weather and other data that you might have access to as well. And so oftentimes we can distill this in terms of just possible events that might happen and what the likelihood of those events are. This comes a lot in games, for example, where there's an element of chance inside of those games. So you imagine rolling a dice. You're not sure exactly what the die roll is going to be, but you know it's going to be one of these possibilities from 1 to 6, for example. And so here now we introduce the idea of probability theory. And what we'll take a look at today is beginning by looking at the mathematical foundations of probability theory, getting an understanding for some of the key concepts within probability, and then diving into how we can use probability and the ideas that we look at mathematically to represent some ideas in terms of models that we can put into our computers in order to program an AI that is able to use information about probability to draw inferences, to make some judgments about the world with some probability or likelihood of being true. So probability ultimately boils down to this idea that there are possible worlds that we're here representing using this little Greek letter omega. And the idea of a possible world is that, when I roll a die, there are 6 possible worlds that could result from it. I could roll a 1 or a 2 or a 3 or a 4 or a 5 or a 6. And each of those are a possible world. And each of those possible worlds has some probability of being true, the probability that I do roll a 1 or a 2 or a 3 or something else. And we represent that probability like this, using the capital letter P, and then in parentheses, what it is that we want the probability of. So this right here would be the probability of some possible world as represented by the little letter omega. Now, there are a couple of basic axioms of probability that become relevant as we consider how we deal with probability and how we think about it. First and foremost, every probability value must range between 0 and 1 inclusive. So the smallest value any probability can have is the number 0, which is an impossible event. Something like I roll a die, and the die is a 7 is the roll that I get. If the die only has numbers 1 through 6, the event that I roll a 7 is impossible, so it would have probability 0. And on the other end of the spectrum, probability can range all the way up to the positive number 1, meaning an event is certain to happen. That I roll a die and the number is less than 10, for example. That is an event that is guaranteed to happen if the only sides on my die are 1 through 6, for instance. And then they can range through any real number in between these two values, where generally speaking, a higher value for the probability means an event is more likely to take place, and a lower value for the probability means the event is less likely to take place. And the other key rule for probability looks a little bit like this. This sigma notation, if you haven't seen it before, refers to summation, the idea that we're going to be adding up a whole sequence of values. And this sigma notation is going to come up a couple of times today, because as we deal with probability, oftentimes we're adding up a whole bunch of individual values or individual probabilities to get some other value. So we'll see this come up a couple of times. But what this notation means is that if I sum up all of the possible worlds omega that are in big omega, which represents the set of all the possible worlds, meaning I take for all of the worlds in the set of possible worlds and add up all of their probabilities, what I ultimately get is the number 1. So if I take all the possible worlds, add up what each of their probabilities is, I should get the number 1 at the end, meaning all probabilities just need to sum to 1. So for example, if I take dice, for example, if you imagine I have a fair die with numbers 1 through 6, and I roll the die, each one of these rolls has an equal probability of taking place, and the probability is 1 over 6, for example. So each of these probabilities is between 0 and 1, 0 meaning impossible, and 1 meaning for certain. And if you add up all of these probabilities for all of the possible worlds, you get the number 1. And we can represent any one of those probabilities like this. The probability that we roll the number 2, for example, is just 1 over 6. Every 6 times we roll the die, we'd expect that 1 time, for instance, the die might come up as a 2. Its probability is not certain, but it's a little more than nothing, for instance. And so this is all fairly straightforward for just a single die. But things get more interesting as our models of the world get a little bit more complex. Let's imagine now that we're not just dealing with a single die, but we have 2 dice, for example. I have a red die here and a blue die there. And I care not just about what the individual roll is, but I care about the sum of the 2 rolls. In this case, the sum of the 2 rolls is the number 3. How do I begin to now reason about what does the probability look like if instead of having 1 die, I now have 2 dice? Well, what we might imagine is that we could first consider what are all of the possible worlds. And in this case, all of the possible worlds are just every combination of the red and blue die that I could come up with. For the red die, it could be a 1 or a 2 or a 3 or a 4 or a 5 or a 6. And for each of those possibilities, the blue die likewise could also be either 1 or 2 or 3 or 4 or 5 or 6. And it just so happens that in this particular case, each of these possible combinations is equally likely. Equally likely are all of these various different possible worlds. That's not always going to be the case. As you imagine more complex models that we could try to build and things that we could try to represent in the real world, it's probably not going to be the case that every single possible world is always equally likely. But in the case of fair dice, where in any given die roll, any one number has just as good a chance of coming up as any other number, we can consider all of these possible worlds to be equally likely. But even though all of the possible worlds are equally likely, that doesn't necessarily mean that their sums are equally likely. So if we consider what the sum is of all of these two, so 1 plus 1, that's a 2, 2 plus 1 is a 3, and consider for each of these possible pairs of numbers what their sum ultimately is, we can notice that there are some patterns here, where it's not entirely the case that every number comes up equally likely. If you consider 7, for example, what's the probability that when I roll 2 dice, their sum is 7? There are several ways this can happen. There are 6 possible worlds where the sum is 7. It could be a 1 and a 6, or a 2 and a 5, or a 3 and a 4, a 4 and a 3, and so forth. But if you instead consider, what's the probability that I roll 2 dice, and the sum of those 2 die rolls is 12, for example, well, looking at this diagram, there's only one possible world in which that can happen. And that's the possible world where both the red die and the blue die both come up as 6s to give us a sum total of 12. So based on just taking a look at this diagram, we see that some of these probabilities are likely different. The probability that the sum is a 7 must be greater than the probability that the sum is a 12. And we can represent that even more formally by saying, OK, the probability that we sum to 12 is 1 out of 36. Out of the 36 equally likely possible worlds, 6 squared, because we have 6 options for the red die and 6 options for the blue die, out of those 36 options, only one of them sums to 12. Whereas on the other hand, the probability that if we take 2 dice rolls and they sum up to the number 7, well, out of those 36 possible worlds, there were 6 worlds where the sum was 7, and so we get 6 over 36, which we can simplify as a fraction to just 1 over 6. So here now we're able to represent these different ideas of probability, representing some events that might be more likely and then other events that are less likely as well. And these sorts of judgments, where we're figuring out just in the abstract what is the probability that this thing takes place, are generally known as unconditional probabilities. Some degree of belief we have in some proposition, some fact about the world, in the absence of any other evidence. Without knowing any additional information, if I roll a die, what's the chance it comes up as a 2? Or if I roll 2 dice, what's the chance that the sum of those 2 die rolls is a 7? But usually when we're thinking about probability, especially when we're thinking about training an AI to intelligently be able to know something about the world and make predictions based on that information, it's not unconditional probability that our AI is dealing with, but rather conditional probability. Probability where rather than having no original knowledge, we have some initial knowledge about the world and how the world actually works. So conditional probability is the degree of belief in a proposition given some evidence that has already been revealed to us. So what does this look like? Well, it looks like this in terms of notation. We're going to represent conditional probability as probability of A, and then this vertical bar, and then B. And the way to read this is the thing on the left-hand side of the vertical bar is what we want the probability of. Here now, I want the probability that A is true, that it is the real world, that it is the event that actually does take place. And then on the right side of the vertical bar is our evidence, the information that we already know for certain about the world. For example, that B is true. So the way to read this entire expression is what is the probability of A given B? The probability that A is true, given that we already know that B is true. And this type of judgment, conditional probability, the probability of one thing given some other fact, comes up quite a lot when we think about the types of calculations we might want our AI to be able to do. For example, we might care about the probability of rain today, given that we know that it rained yesterday. We could think about the probability of rain today just in the abstract. What is the chance that today it rains? But usually we have some additional evidence. I know for certain that it rained yesterday, and so I would like to calculate the probability that it rains today, given that I know that it rained yesterday. Or you might imagine that I want to know the probability that my optimal route to my destination changes, given the current traffic conditions. So whether or not traffic conditions change, that might change the probability that this route is actually the optimal route. Or you might imagine in a medical context, I want to know the probability that a patient has a particular disease, given some results of some tests that have been performed on that patient. And I have some evidence, the results of that test, and I would like to know the probability that a patient has a particular disease. So this notion of conditional probability comes up everywhere as we begin to think about what we would like to reason about, but being able to reason a little more intelligently by taking into account evidence that we already have. We're more able to get an accurate result for what is the likelihood that someone has this disease if we know this evidence, the results of the test, as opposed to if we were just calculating the unconditional probability of saying, what is the probability they have the disease, without any evidence to try and back up our result one way or the other. So now that we've got this idea of what conditional probability is, the next question we have to ask is, all right, how do we calculate conditional probability? How do we figure out mathematically, if I have an expression like this, how do I get a number from that? What does conditional probability actually mean? Well, the formula for conditional probability looks a little something like this. The probability of A given B, the probability that A is true, given that we know that B is true, is equal to this fraction, the probability that A and B are true, divided by just the probability that B is true. And the way to intuitively try to think about this is that if I want to know the probability that A is true, given that B is true, well, I want to consider all the ways they could both be true out of the only worlds that I care about are the worlds where B is already true. I can sort of ignore all the cases where B isn't true because those aren't relevant to my ultimate computation. They're not relevant to what it is that I want to get information about. So let's take a look at an example. Let's go back to that example of rolling 2 dice and the idea that those 2 dice might sum up to the number 12. We discussed earlier that the unconditional probability that if I roll 2 dice and they sum to 12 is 1 out of 36, because out of the 36 possible worlds that I might care about, in only one of them is the sum of those 2 dice 12. It's only when red is 6 and blue is also 6. But let's say now that I have some additional information. I now want to know what is the probability that the 2 dice sum to 12, given that I know that the red die was a 6. So I already have some evidence. I already know the red die is a 6. I don't know what the blue die is. That information isn't given to me in this expression. But given the fact that I know that the red die rolled a 6, what is the probability that we sum to 12? And so we can begin to do the math using that expression from before. Here again are all of the possibilities, all of the possible combinations of red die being 1 through 6 and blue die being 1 through 6. And I might consider first, all right, what is the probability of my evidence, my B variable, where I want to know what is the probability that the red die is a 6? Well, the probability that the red die is a 6 is just 1 out of 6. So these 1 out of 6 options are really the only worlds that I care about here now. All the rest of them are irrelevant to my calculation because I already have this evidence that the red die was a 6, so I don't need to care about all of the other possibilities that could result. So now, in addition to the fact that the red die rolled as a 6 and the probability of that, the other piece of information I need to know in order to calculate this conditional probability is the probability that both of my variables, A and B, are true. The probability that both the red die is a 6 and they all sum to 12. So what is the probability that both of these things happen? Well, it only happens in one possible case, in 1 out of these 36 cases, and it's the case where both the red and the blue die are equal to 6. This is a piece of information that we already knew. And so this probability is equal to 1 over 36. And so to get the conditional probability that the sum is 12, given that I know that the red dice is equal to 6, well, I just divide these two values together, and 1 over 36 divided by 1 over 6 gives us this probability of 1 over 6. Given that I know that the red die rolled a value of 6, the probability that the sum of the two dice is 12 is also 1 over 6. And that probably makes intuitive sense to you too, because if the red die is a 6, the only way for me to get to a 12 is if the blue die also rolls a 6, and we know that the probability of the blue die rolling a 6 is 1 over 6. So in this case, the conditional probability seems fairly straightforward, but this idea of calculating a conditional probability by looking at the probability that both of these events take place is an idea that's going to come up again and again. This is the definition now of conditional probability, and we're going to use that definition as we think about probability more generally to be able to draw conclusions about the world. This, again, is that formula. The probability of A given B is equal to the probability that A and B take place divided by the probability of B. And you'll see this formula sometimes written in a couple of different ways. You could imagine algebraically multiplying both sides of this equation by probability of B to get rid of the fraction. And you'll get an expression like this. The probability of A and B, which is this expression over here, is just the probability of B times the probability of A given B. Or you could represent this equivalently, since A and B in this expression are interchangeable. A and B is the same thing as B and A. You could imagine also representing the probability of A and B as the probability of A times the probability of B given A, just switching all of the A's and B's. These three are all equivalent ways of trying to represent what joint probability means. And so you'll sometimes see all of these equations, and they might be useful to you as you begin to reason about probability and to think about what values might be taking place in the real world. Now, sometimes when we deal with probability, we don't just care about a Boolean event, like did this happen or did this not happen. Sometimes we might want the ability to represent like variable values in a probability space, where some variable might take on multiple different possible values. And in probability, we call a variable in probability theory a random variable. A random variable in probability is just some variable in probability theory that has some domain of values that it can take on. So what do I mean by this? Well, what I mean is I might have a random variable that is just called roll, for example, that has 6 possible values. Roll is my variable, and the possible values, the domain of values that it can take on, are 1, 2, 3, 4, 5, and 6. And I might like to know the probability of each. In this case, they happen to all be the same. But in other random variables, that might not be the case. For example, I might have a random variable to represent the weather, for example, where the domain of values it could take on are things like sun or cloudy or rainy or windy or snowy. And each of those might have a different probability. And I care about knowing what is the probability that the weather equals sun or that the weather equals clouds, for instance. And I might like to do some mathematical calculations based on that information. Other random variables might be something like traffic. What are the odds that there is no traffic or light traffic or heavy traffic? Traffic in this case is my random variable, and the values that that random variable can take on are here. It's either none or light or heavy. And I, the person doing these calculations, I, the person encoding these random variables into my computer, need to make the decision as to what these possible values actually are. You might imagine, for example, for a flight, if I care about whether or not I make it into a flight on time, my flight has a couple of possible values that it could take on. My flight could be on time, my flight could be delayed, my flight could be canceled. So flight, in this case, is my random variable, and these are the values that it can take on. And often I'll want to know something about the probability that my random variable takes on each of those possible values. And this is what we then call a probability distribution. A probability distribution takes a random variable and gives me the probability for each of the possible values in its domain. So in the case of this flight, for example, my probability distribution might look something like this. My probability distribution says the probability that the random variable flight is equal to the value on time is 0.6. Or otherwise, put into more English human-friendly terms, the likelihood that my flight is on time is 60%, for example. And in this case, the probability that my flight is delayed is 30%. The probability that my flight is canceled is 10% or 0.1. And if you sum up all of these possible values, the sum is going to be 1, right? If you take all of the possible worlds, here are my 3 possible worlds for the value of the random variable flight, add them all up together, the result needs to be the number 1 per that axiom of probability theory that we've discussed before. So this now is one way of representing this probability distribution for the random variable flight. Sometimes you'll see it represented a little bit more concisely, that this is pretty verbose for really just trying to express 3 possible values. And so often you'll instead see this same notation representing using a vector. And all a vector is a sequence of values. As opposed to just a single value, I might have multiple values. And so I could instead represent this idea this way. Bold p, so a larger p, generally meaning the probability distribution of this variable flight is equal to this vector represented in angle brackets. The probability distribution is 0.6, 0.3, and 0.1. And I would just have to know that this probability distribution is in order of on time or delayed and canceled to know how to interpret this vector, to mean the first value in the vector is the probability that my flight is on time. The second value in the vector is the probability that my flight is delayed. And the third value in the vector is the probability that my flight is canceled. And so this is just an alternate way of representing this idea a little more verbosely. But oftentimes, you'll see us just talk about a probability distribution over a random variable. And whenever we talk about that, what we're really doing is trying to figure out the probabilities of each of the possible values that that random variable can take on. But this notation is just a little bit more succinct, even though it can sometimes be a little confusing depending on the context in which you see it. So we'll start to look at examples where we use this sort of notation to describe probability and to describe events that might take place. A couple of other important ideas to know with regards to probability theory. One is this idea of independence. And independence refers to the idea that the knowledge of one event doesn't influence the probability of another event. So for example, in the context of my 2 dice rolls, where I had the red die and the blue die, the probability that I roll the red die and the blue die, those 2 events, red die and blue die, are independent. Knowing the result of the red die doesn't change the probabilities for the blue die. It doesn't give me any additional information about what the value of the blue die is ultimately going to be. But that's not always going to be the case. You might imagine that in the case of weather, something like clouds and rain, those are probably not independent. That if it is cloudy, that might increase the probability that later in the day it's going to rain. So some information informs some other event or some other random variable. So independence refers to the idea that one event doesn't influence the other. And if they're not independent, then there might be some relationship. So mathematically, formally, what does independence actually mean? Well, recall this formula from before, that the probability of A and B is the probability of A times the probability of B given A. And the more intuitive way to think about this is that to know how likely it is that A and B happen, well, let's first figure out the likelihood that A happens. And then given that we know that A happens, let's figure out the likelihood that B happens and multiply those 2 things together. But if A and B were independent, meaning knowing A doesn't change anything about the likelihood that B is true, well, then the probability of B given A, meaning the probability that B is true, given that I know A is true, well, that I know A is true shouldn't really make a difference if these 2 things are independent. That A shouldn't influence B at all. So the probability of B given A is really just the probability of B, if it is true that A and B are independent. And so this right here is one example of a definition for what it means for A and B to be independent. The probability of A and B is just the probability of A times the probability of B. Anytime you find 2 events A and B where this relationship holds, then you can say that A and B are independent. So an example of that might be the dice that we were taking a look at before. Here, if I wanted the probability of red being a 6 and blue being a 6, well, that's just the probability that red is a 6 multiplied by the probability that blue is a 6. It's both equal to 1 over 36. So I can say that these 2 events are independent. What wouldn't be independent, for example, would be an example. So this, for example, has a probability of 1 over 36, as we talked about before. But what wouldn't be independent would be a case like this. The probability that the red die rolls a 6 and the red die rolls a 4. If you just naively took, OK, red die 6, red die 4, Well, if I'm only rolling the die once, you might imagine the naive approach is to say, well, each of these has a probability of 1 over 6, so multiply them together, and the probability is 1 over 36. But of course, if you're only rolling the red die once, there's no way you could get two different values for the red die. It couldn't both be a 6 and a 4, so the probability should be 0. But if you were to multiply probability of red 6 times probability of red 4, well, that would equal 1 over 36. But of course, that's not true, because we know that there is no way, probability 0, that when we roll the red die once, we get both a 6 and a 4, because only one of those possibilities can actually be the result. And so we can say that the event that red roll is 6 and the event that red roll is 4, those two events are not independent. If I know that the red roll is a 6, I know that the red roll cannot possibly be a 4. So these things are not independent. And instead, if I wanted to calculate the probability, I would need to use this conditional probability, as is the regular definition of the probability of two events taking place. And the probability of this now, well, the probability of the red roll being a 6, that's 1 over 6. But what's the probability that the roll is a 4, given that the roll is a 6? Well, this is just 0, because there's no way for the red roll to be a 4, given that we already know the red roll is a 6. And so the value, if we do out all that multiplication, is we get the number 0. So this idea of conditional probability is going to come up again and again, especially as we begin to reason about multiple different random variables that might be interacting with each other in some way. And this gets us to one of the most important rules in probability theory, which is known as Bayes' rule. And it turns out that just using the information we've already learned about probability and just applying a little bit of algebra, we can actually derive Bayes' rule for ourselves. But it's a very important rule when it comes to inference and thinking about probability in the context of what it is that a computer can do, or what a mathematician could do, by having access to information about probability. So let's go back to these equations to be able to derive Bayes' rule ourselves. We know the probability of A and B, the likelihood that A and B take place, is the likelihood of B, and then the likelihood of A, given that we know that B is already true. And likewise, the probability of A given A and B is the probability of A times the probability of B, given that we know that A is already true. This is sort of a symmetric relationship where it doesn't matter the order of A and B and A mean the same thing. And so in these equations, we can just swap out A and B to be able to represent the exact same idea. So we know that these two equations are already true. We've seen that already. And now let's just do a little bit of algebraic manipulation of this stuff. Both of these expressions on the right-hand side are equal to the probability of A and B. So what I can do is take these two expressions on the right-hand side and just set them equal to each other. Right? If they're both equal to the probability of A and B, then they both must be equal to each other. So probability of A times probability of B given A is equal to the probability of B times the probability of A given B. And now all we're going to do is do a little bit of division. I'm going to divide both sides by P of A. And now I get what is Bayes' rule. The probability of B given A is equal to the probability of B times the probability of A given B divided by the probability of A. And sometimes in Bayes' rule, you'll see the order of these two arguments switched. So instead of B times A given B, it'll be A given B times B. That ultimately doesn't matter, because in multiplication, you can switch the order of the two things you're multiplying, and it doesn't change the result. But this here right now is the most common formulation of Bayes' rule. The probability of B given A is equal to the probability of A given B times the probability of B divided by the probability of A. And this rule, it turns out, is really important when it comes to trying to infer things about the world, because it means you can express one conditional probability, the conditional probability of B given A, using knowledge about the probability of A given B, using the reverse of that conditional probability. So let's first do a little bit of an example with this, just to see how we might use it, and then explore what this means a little bit more generally. So we're going to construct a situation where I have some information. There are two events that I care about. The idea that it's cloudy in the morning, and the idea that it is rainy in the afternoon. Those are two different possible events that could take place. Cloudy in the morning, or the AM, rainy in the PM. And what I care about is, given clouds in the morning, what is the probability of rain in the afternoon? A reasonable question I might ask. In the morning, I look outside, or an AI's camera looks outside and sees that there are clouds in the morning. And we want to figure out what is the probability that in the afternoon there is going to be rain. Of course, in the abstract, we don't have access to this kind of information, but we can use data to begin to try and figure this out. So let's imagine now that I have access to some pieces of information. I have access to the idea that 80% of rainy afternoons start out with a cloudy morning. And you might imagine that I could have gathered this data just by looking at data over a sequence of time, that I know that 80% of the time, when it's raining in the afternoon, it was cloudy that morning. I also know that 40% of days have cloudy mornings. And I also know that 10% of days have rainy afternoons. And now using this information, I would like to figure out, given clouds in the morning, what is the probability that it rains in the afternoon? I want to know the probability of afternoon rain given morning clouds. And I can do that in particular using this fact, the probability of so if I know that 80% of rainy afternoons start with cloudy mornings, then I know the probability of cloudy mornings given rainy afternoons. So using sort of the reverse conditional probability, I can figure that out. Expressed in terms of Bayes' rule, this is what that would look like. Probability of rain given clouds is the probability of clouds given rain times the probability of rain divided by the probability of clouds. Here I'm just substituting in for the values of A and B from that equation of Bayes' rule from before, and then I can just do the math. I have this information. I know that 80% of the time, if it was raining, then there were clouds in the morning, so 0.8 here. The probability of rain is 0.1, because 10% of days were rainy and 40% of days were cloudy. I do the math, and I can figure out the answer is 0.2. So the probability that it rains in the afternoon, given that it was cloudy in the morning, is 0.2 in this case. And this now is an application of Bayes' rule, the idea that using one conditional probability, we can get the reverse conditional probability. And this is often useful when one of the conditional probabilities might be easier for us to know about or easier for us to have data about. And using that information, we can calculate the other conditional probability. So what does this look like? Well, it means that knowing the probability of cloudy mornings given rainy afternoons, we can calculate the probability of rainy afternoons given cloudy mornings. Or, for example, more generally, if we know the probability of some visible effect, some effect that we can see and observe, given some unknown cause that we're not sure about, well, then we can calculate the probability of that unknown cause given the visible effect. So what might that look like? Well, in the context of medicine, for example, I might know the probability of some medical test result given a disease. Like I know that if someone has a disease, then X% of the time, the medical test result will show up as this, for instance. And using that information, then I can calculate, all right, what is the probability that given I know the medical test result, what is the likelihood that someone has the disease? This is the piece of information that is usually easier to know, easier to immediately have access to data for. And this is the information that I actually want to calculate. Or I might want to know, for example, if I know that some probability of counterfeit bills have like blurry text around the edges, because counterfeit printers aren't nearly as good at printing text precisely. So I have some information about, given that something is a counterfeit bill, like X% of counterfeit bills have blurry text, for example. And using that information, then I can calculate some piece of information that I might want to know, like given that I know there's blurry text on a bill, what is the probability that that bill is counterfeit? So given one conditional probability, I can calculate the other conditional probability as well. And so now we've taken a look at a couple of different types of probability. We've looked at unconditional probability, where I just look at what is the probability of this event occurring, given no additional evidence that I might have access to. And we've also looked at conditional probability, where I have some sort of evidence, and I would like to, using that evidence, be able to calculate some other probability as well. The other kind of probability that will be important for us to think about is joint probability. And this is when we're considering the likelihood of multiple different events simultaneously. And so what do we mean by this? Well, for example, I might have probability distributions that look a little something like this. Like, I want to know the probability distribution of clouds in the morning. And that distribution looks like this. 40% of the time, c, which is my random variable here, is equal to it's cloudy. And 60% of the time, it's not cloudy. So here is just a simple probability distribution that is effectively telling me that 40% of the time, it's cloudy. I might also have a probability distribution for rain in the afternoon, where 10% of the time, or with probability 0.1, it is raining in the afternoon, and with probability 0.9, it is not raining in the afternoon. And using just these two pieces of information, I don't actually have a whole lot of information about how these two variables relate to each other. But I could if I had access to their joint probability, meaning for every combination of these two things, meaning morning cloudy and afternoon rain, morning cloudy and afternoon not rain, morning not cloudy and afternoon rain, and morning not cloudy and afternoon not raining, if I had access to values for each of those four, I'd have more information. So information that'd be organized in a table like this, and this, rather than just a probability distribution, is a joint probability distribution. It tells me the probability distribution of each of the possible combinations of values that these random variables can take on. So if I want to know what is the probability that on any given day it is both cloudy and rainy, well, I would say, all right, we're looking at cases where it is cloudy and cases where it is raining, and the intersection of those two, that row and that column, is 0.08. So that is the probability that it is both cloudy and rainy using that information. And using this conditional probability table, or using this joint probability table, I can begin to draw other pieces of information about things like conditional probability. So I might ask a question like, what is the probability distribution of clouds given that I know that it is raining? Meaning I know for sure that it's raining. Tell me the probability distribution over whether it's cloudy or not, given that I know already that it is in fact raining. And here I'm using C to stand for that random variable. I'm looking for a distribution, meaning the answer to this is not going to be a single value. It's going to be two values, a vector of two values, where the first value is probability of clouds, the second value is probability that it is not cloudy, but the sum of those two values is going to be 1, because when you add up the probabilities of all of the possible worlds, the result that you get must be the number 1. And well, what do we know about how to calculate a conditional probability? Well, we know that the probability of A given B is the probability of A and B divided by the probability of B. So what does this mean? Well, it means that I can calculate the probability of clouds given that it's raining as the probability of clouds and raining divided by the probability of rain. And this comma here for the probability distribution of clouds and rain, this comma sort of stands in for the word and. You'll sort of see the logical operator and the comma used interchangeably. This means the probability distribution over the clouds and knowing the fact that it is raining divided by the probability of rain. And the interesting thing to note here, and what we'll often do in order to simplify our mathematics, is that dividing by the probability of rain, the probability of rain here is just some numerical constant. It is some number. Dividing by probability of rain is just dividing by some constant, or in other words, multiplying by the inverse of that constant. And it turns out that oftentimes we can just not worry about what the exact value of this is, and just know that it is, in fact, a constant value. And we'll see why in a moment. So instead of expressing this as this joint probability divided by the probability of rain, sometimes we'll just represent it as alpha times the numerator here, the probability distribution of C, this variable, and that we know that it is raining, for instance. So all we've done here is said this value of 1 over the probability of rain, that's really just a constant that we're going to divide by or equivalently multiply by the inverse of at the end. We'll just call it alpha for now and deal with it a little bit later. But the key idea here now, and this is an idea that's going to come up again, is that the conditional distribution of C given rain is proportional to, meaning just some factor multiplied by, the joint probability of C and rain being true. And so how do we figure this out? Well, this is going to be the probability that it is cloudy given that it's rainy, which is 0.08, and the probability that it's not cloudy given that it's rainy, which is 0.02. And so we get alpha times here now is that probability distribution. 0.08 is clouds and rain. 0.02 is not cloudy and rain. But of course, 0.08 and 0.02 don't sum up to the number 1. And we know that in a probability distribution, if you consider all of the possible values, they must sum up to a probability of 1. And so we know that we just need to figure out some constant to normalize, so to speak, these values, something we can multiply or divide by to get it so that all these probabilities sum up to 1. And it turns out that if we multiply both numbers by 10, then we can get that result of 0.8 and 0.2. The proportions are still equivalent, but now 0.8 plus 0.2, those sum up to the number 1. So take a look at this and see if you can understand step by step how it is we're getting from one point to another. But the key idea here is that by using the joint probabilities, these probabilities that it is both cloudy and rainy, and that it is not cloudy and rainy, I can take that information and figure out the conditional probability, given that it's raining. What is the chance that it's cloudy versus not cloudy? Just by multiplying by some normalization constant, so to speak. And this is what a computer can begin to use to be able to interact with these various different types of probabilities. And it turns out there are a number of other probability rules that are going to be useful to us as we begin to explore how we can actually use this information to encode into our computers some more complex analysis that we might want to do about probability and distributions and random variables that we might be interacting with. So here are a couple of those important probability rules. One of the simplest rules is just this negation rule. What is the probability of not event A? So A is an event that has some probability, and I would like to know what is the probability that A does not occur. And it turns out it's just 1 minus P of A, which makes sense, because if those are the two possible cases, either A happens or A doesn't happen, then when you add up those two cases, you must get 1, which means P of not A must just be 1 minus P of A, because P of A and P of not A must sum up to the number 1. They must include all of the possible cases. We've seen an expression for calculating the probability of A and B. We might also reasonably want to calculate the probability of A or B. What is the probability that one thing happens or another thing happens? So for example, I might want to calculate what is the probability that if I roll 2 dice, a red die and a blue die, what is the likelihood that A is a 6 or B is a 6, like one or the other? And what you might imagine you could do, and the wrong way to approach it, would be just to say, all right, well, A comes up as a 6 with the red die comes up as a 6 with probability 1 over 6. The same for the blue die. It's also 1 over 6. Add them together, and you get 2 over 6, otherwise known as 1/3. But this suffers from a problem of overcounting, that we've double counted the case where both A and B, both the red die and the blue die, both come up as a 6 roll. And I've counted that instance twice. So to resolve this, the actual expression for calculating the probability of A or B uses what we call the inclusion-exclusion formula. So I take the probability of A, add it to the probability of B, that's all same as before, but then I need to exclude the cases that I've double counted. So I subtract from that the probability of A and B. And that gets me the result for A or B. I consider all the cases where A is true and all the cases where B is true. And if you imagine this is like a Venn diagram of cases where A is true, cases where B is true, I just need to subtract out the middle to get rid of the cases that I have overcounted by double counting them inside of both of these individual expressions. One other rule that's going to be quite helpful is a rule called marginalization. So marginalization is answering the question of how do I figure out the probability of A using some other variable that I might have access to, like B. Even if I don't know additional information about it, I know that B, some event, can have two possible states. Either B happens or B doesn't happen, assuming it's a Boolean, true or false. And well, what that means is that for me to be able to calculate the probability of A, there are only two cases. Either A happens and B happens, or A happens and B doesn't happen. And those are two disjoint, meaning they can't both happen together. Either B happens or B doesn't happen. They're disjoint or separate cases. And so I can figure out the probability of A just by adding up those two cases. The probability that A is true is the probability that A and B is true, plus the probability that A is true and B isn't true. So by marginalizing, I've looked at the two possible cases that might take place. Either B happens or B doesn't happen. And in either of those cases, I look at what's the probability that A happens. And if I add those together, well, then I get the probability that A happens as a whole. So take a look at that rule. It doesn't matter what B is or how it's related to A. So long as I know these joint distributions, I can figure out the overall probability of A. And this can be a useful way if I have a joint distribution, like the joint distribution of A and B, to just figure out some unconditional probability, like the probability of A. And we'll see examples of this soon as well. Now, sometimes these might not just be variables that are events that are like they happened or they didn't happen, like B is here. They might be some broader probability distribution where there are multiple possible values. And so here, in order to use this marginalization rule, I need to sum up not just over B and not B, but for all of the possible values that the other random variable could take on. And so here we'll see a version of this rule for random variables, and it's going to include that summation notation to indicate that I'm summing up, adding up a whole bunch of individual values. So here's the rule. Looks a lot more complicated, but it's actually the equivalent, exactly the same rule. What I'm saying here is that if I have two random variables, one called x and one called y, well, the probability that x is equal to some value x sub I, this is just some value that this variable takes on, how do I figure it out? Well, I'm going to sum up over j, where j is going to range over all of the possible values that y can take on. Well, let's look at the probability that x equals xi and y equals yj. So the exact same rule. The only difference here is now I'm summing up over all of the possible values that y can take on, saying let's add up all of those possible cases and look at this joint distribution, this joint probability that x takes on the value I care about, given all of the possible values for y. And if I add all those up, then I can get this unconditional probability of what x is equal to, whether or not x is equal to some value x sub I. So let's take a look at this rule, because it does look a little bit complicated. Let's try and put a concrete example to it. Here again is that same joint distribution from before. I have cloud, not cloudy, rainy, not rainy. And maybe I want to access some variable. I want to know what is the probability that it is cloudy. Well, marginalization says that if I have this joint distribution and I want to know, like, what is the probability that it is cloudy, well, I need to consider the other variable, the variable that's not here, the idea that it's rainy. And I consider the two cases. Either it's raining or it's not raining. And I just sum up the values for each of those possibilities. In other words, the probability that it is cloudy is equal to the sum of the probability that it's cloudy and it's rainy, and the probability that it's cloudy and it is not raining. And so these now are values that I have access to. These are values that are just inside of this joint probability table. What is the probability that it is both cloudy and rainy? Well, it's just the intersection of these two here, which is 0.08. And the probability that it's cloudy and not raining is, all right, here's cloudy, here's not raining. It's 0.32. So it's 0.08 plus 0.32, which just gives us equal to 0.4. That is the unconditional probability that it is, in fact, cloudy. And so marginalization gives us a way to go from these joint distributions to just some individual probability that I might care about. And you'll see a little bit later why it is that we care about that and why that's actually useful to us as we begin doing some of these calculations. Last rule we'll take a look at before transitioning to something a little bit different is this rule of conditioning, very similar to the marginalization rule. But it says that, again, if I have two events A and B, but instead of having access to their joint probabilities, I have access to their conditional probabilities, how they relate to each other. Well, again, if I want to know the probability that A happens, and I know that there's some other variable B, either B happens or B doesn't happen, and so I can say that the probability of A is the probability of A given B times the probability of B, meaning B happened, and given that I know B happened, what's the likelihood that A happened? And then I consider the other case, that B didn't happen. So here's the probability that B didn't happen, and here's the probability that A happens, given that I know that B didn't happen. And this is really the equivalent rule, just using conditional probability instead of joint probability, where I'm saying let's look at both of these two cases and condition on B. Look at the case where B happens, and look at the case where B doesn't happen, and look at what probabilities I get as a result. And just as in the case of marginalization, where there was an equivalent rule for random variables that could take on multiple possible values in a domain of possible values, here too conditioning has the same equivalent rule. Again, there's a summation to mean I'm summing over all of the possible values that some random variable y could take on. But if I want to know what is the probability that x takes on this value, then I'm going to sum up over all the values j that y could take on. and say, all right, what's the chance that y takes on that value, yj, and multiply it by the conditional probability that x takes on this value given that y took on that value, yj. So equivalent rule, just using conditional probabilities instead of joint probabilities. And using the equation we know about joint probabilities, we can translate between these two. So all right, we've seen a whole lot of mathematics, and we've just sort of laid the foundation for mathematics. And no need to worry if you haven't seen probability in too much detail up until this point. These are sort of the foundations of the ideas that are going to come up as we begin to explore how we can now take these ideas from probability and begin to apply them to represent something inside of our computer, something inside of the AI agent we're trying to design that is able to represent information and probabilities and the likelihoods between various different events. So there are a number of different probabilistic models that we can generate. But the first of the models we're going to talk about are what are known as Bayesian networks. And a Bayesian network is just going to be some network of random variables, connected random variables, that are going to represent the dependence between these random variables. That odds are most random variables in this world are not independent from each other, that there's some relationship between things that are happening that we care about. If it is rainy today, that might increase the likelihood that my flight or my train gets delayed, for example. There's some dependence between these random variables, and a Bayesian network is going to be able to capture those dependencies. So what is a Bayesian network? What is its actual structure, and how does it work? Well, a Bayesian network is going to be a directed graph. And again, we've seen directed graphs before. They are individual nodes with arrows or edges that connect one node to another node, pointing in a particular direction. And so this directed graph is going to have nodes as well, where each node in this directed graph is going to represent a random variable, something like the weather, or something like whether my train was on time or delayed. And we're going to have an arrow from a node x to a node y to mean that x is a parent of y. So that'll be our notation. If there's an arrow from x to y, x is going to be considered a parent of y. And the reason that's important is because each of these nodes is going to have a probability distribution that we're going to store along with it, which is the distribution of x given some evidence, given the parents of x. So the way to more intuitively think about this is that the parents can be thought of as sort of causes for some effect that we're going to observe. And so let's take a look at an actual example of a Bayesian network and think about the types of logic that might be involved in reasoning about that network. Let's imagine for a moment that I have an appointment out of town, and I need to take a train in order to get to that appointment. So what are the things I might care about? Well, I care about getting to my appointment on time. Either I make it to my appointment and I'm able to attend it, or I miss the appointment. And you might imagine that that's influenced by the train, that the train is either on time or it's delayed, for example. But that train itself is also influenced. Whether the train is on time or not depends maybe on the rain. Is there no rain? Is it light rain? Is there heavy rain? And it might also be influenced by other variables too. It might be influenced as well by whether or not there's maintenance on the train track, for example. If there is maintenance on the train track, that probably increases the likelihood that my train is delayed. And so we can represent all of these ideas using a Bayesian network that looks a little something like this. Here I have 4 nodes representing 4 random variables that I would like to keep track of. I have one random variable called rain that can take on 3 possible values in its domain, either none or light or heavy, for no rain, light rain, or heavy rain. I have a variable called maintenance for whether or not there's maintenance on the train track, which it has 2 possible values, just either yes or no. Either there is maintenance or there's no maintenance happening on the track. Then I have a random variable for the train, indicating whether or not the train was on time or not. That random variable has 2 possible values in its domain. The train is either on time or the train is delayed. And then finally, I have a random variable for whether I make it to my appointment. For my appointment down here, I have a random variable called appointment that itself has 2 possible values, attend and miss. And so here are the possible values. Here are my 4 nodes, each of which represents a random variable, each of which has a domain of possible values that it can take on. And the arrows, the edges pointing from one node to another, encode some notion of dependence inside of this graph. That whether I make it to my appointment or not is dependent upon whether the train is on time or delayed. And whether the train is on time or delayed is dependent on 2 things, given by the 2 arrows pointing at this node. It is dependent on whether or not there was maintenance on the train track, and it is also dependent upon whether or not it was raining, or whether it is raining. And just to make things a little complicated, let's say as well that whether or not there's maintenance on the track, this too might be influenced by the rain. That if there's heavier rain, well, maybe it's less likely that there's going to be maintenance on the train track that day because they're more likely to want to do maintenance on the track on days when it's not raining, for example. And so these nodes might have different relationships between them. But the idea is that we can come up with a probability distribution for any of these nodes based only upon its parents. And so let's look node by node at what this probability distribution might actually look like. And we'll go ahead and begin with this root node, this rain node here, which is at the top and has no arrows pointing into it, which means its probability distribution is not going to be a conditional distribution. It's not based on anything. I just have some probability distribution over the possible values for the rain random variable. And that distribution might look a little something like this. None, light, and heavy each have a possible value. Here I'm saying the likelihood of no rain is 0.7, of light rain is 0.2, of heavy rain is 0.1, for example. So here is a probability distribution for this root node in this Bayesian network. And let's now consider the next node in the network, maintenance. Track maintenance is yes or no. And the general idea of what this distribution is going to encode, at least in this story, is the idea that the heavier the rain is, the less likely it is that there's going to be maintenance on the track, because the people that are doing maintenance on the track probably want to wait until a day when it's not as rainy in order to do the track maintenance, for example. And so what might that probability distribution look like? Well, this now is going to be a conditional probability distribution. That here are the three possible values for the rain random variable, which I'm here just going to abbreviate to R, either no rain, light rain, or heavy rain. And for each of those possible values, either there is yes track maintenance or no track maintenance, and those have probabilities associated with them. That I see here that if it is not raining, then there is a probability of 0.4 that there's track maintenance and a probability of 0.6 that there isn't. But if there's heavy rain, then here the chance that there is track maintenance is 0.1, and the chance that there is not track maintenance is 0.9. Each of these rows is going to sum up to 1, because each of these represent different values of whether or not it's raining, the three possible values that that random variable can take on, and each is associated with its own probability distribution that is ultimately all going to add up to the number 1. So that there is our distribution for this random variable called maintenance, about whether or not there is maintenance on the train track. And now let's consider the next variable. Here we have a node inside of our Bayesian network called train that has two possible values, on time and delayed. And this node is going to be dependent upon the two nodes that are pointing towards it. That this, whether or not the train is on time or delayed, depends on whether or not there's track maintenance, and it depends on whether or not there's rain. That heavier rain probably means more likely that my train is delayed. And if there is track maintenance, that also probably means it's more likely that my train is delayed as well. And so you could construct a larger probability distribution, a conditional probability distribution, that instead of conditioning on just one variable, as was the case here, is now conditioning on two variables, conditioning both on rain, represented by R, and on maintenance, represented by yes. Again, each of these rows has two values that sum up to the number 1, one for whether the train is on time, one for whether the train is delayed. And here I can say something like, all right, if I know there was light rain and track maintenance, well, OK, that would be R is light and M is yes. Well, then there's a probability of 0.6 that my train is on time, and a probability of 0.4 that the train is delayed. And you can imagine gathering this data just by looking at real-world data, looking at data about, all right, if I knew that it was light rain and there was track maintenance, how often was a train delayed or not delayed? And you could begin to construct this thing. But the interesting thing is intelligently being able to try to figure out how might you go about ordering these things, what things might influence other nodes inside of this Bayesian network. And the last thing I care about is whether or not I make it to my appointment. So did I attend or miss the appointment? And ultimately, whether I attend or miss the appointment, it is influenced by track maintenance, because it's indirectly this idea that, all right, if there is track maintenance, well, then my train might more likely be delayed. And if my train is more likely to be delayed, then I'm more likely to miss my appointment. But what we encode in this Bayesian network are just what we might consider to be more direct relationships. So the train has a direct influence on the appointment. And given that I know whether the train is on time or delayed, knowing whether there's track maintenance isn't going to give me any additional information that I didn't already have. That if I know train, these other nodes that are up above isn't really going to influence the result. And so here we might represent it using another conditional probability distribution that looks a little something like this. The train can take on two possible values. Either my train is on time or my train is delayed. And for each of those two possible values, I have a distribution for what are the odds that I'm able to attend the meeting and what are the odds that I miss the meeting. And obviously, if my train is on time, I'm much more likely to be able to attend the meeting than if my train is delayed, in which case I'm more likely to miss that meeting. So all of these nodes put all together here represent this Bayesian network, this network of random variables whose values I ultimately care about, and that have some sort of relationship between them, some sort of dependence where these arrows from one node to another indicate some dependence, that I can calculate the probability of some node given the parents that happen to exist there. So now that we've been able to describe the structure of this Bayesian network and the relationships between each of these nodes by associating each of the nodes in the network with a probability distribution, whether that's an unconditional probability distribution in the case of this root node here, like rain, and a conditional probability distribution in the case of all of the other nodes whose probabilities are dependent upon the values of their parents, we can begin to do some computation and calculation using the information inside of that table. So let's imagine, for example, that I just wanted to compute something simple like the probability of light rain. How would I get the probability of light rain? Well, rain here is a root node. And so if I wanted to calculate that probability, I could just look at the probability distribution for rain and extract from it the probability of light rain. It's just a single value that I already have access to. But we could also imagine wanting to compute more complex joint probabilities, like the probability that there is light rain and also no track maintenance. This is a joint probability of two values, light rain and no track maintenance. And the way I might do that is first by starting by saying, all right, well, let me get the probability of light rain. But now I also want the probability of no track maintenance. But of course, this node is dependent upon the value of rain. So what I really want is the probability of no track maintenance, given that I know that there was light rain. And so the expression for calculating this idea, that the probability of light rain and no track maintenance, is really just the probability of light rain and the probability that there's no track maintenance, given that I know that there already is light rain. So I take the unconditional probability of light rain, multiply it by the conditional probability of no track maintenance, given that I know there's light rain. And you can continue to do this again and again for every variable that you want to add into this joint probability that I might want to calculate. If I wanted to know the probability of light rain and no track maintenance and a delayed train, well, that's going to be the probability of light rain multiplied by the probability of no track maintenance given light rain, multiplied by the probability of a delayed train given light rain and no track maintenance, because whether the train is on time or delayed is dependent upon both of these other two variables. And so I have two pieces of evidence that go into the calculation of that conditional probability. And each of these three values is just a value that I can look up by looking at one of these individual probability distributions that is encoded into my Bayesian network. And if I wanted a joint probability over all four of the variables, something like the probability of light rain and no track maintenance and a delayed train and I miss my appointment, well, that's going to be multiplying four different values, one from each of these individual nodes. It's going to be the probability of light rain, then of no track maintenance given light rain, then of a delayed train given light rain and no track maintenance, and then finally, for this node here, for whether I make it to my appointment or not, it's not dependent upon these two variables, given that I know whether or not the train is on time. I only need to care about the conditional probability that I miss my train, or that I miss my appointment, given that the train happens to be delayed. And so that's represented here by four probabilities, each of which is located inside of one of these probability distributions for each of the nodes, all multiplied together. And so I can take a variable like that and figure out what the joint probability is by multiplying a whole bunch of these individual probabilities from the Bayesian network. But of course, just as with last time, where what I really wanted to do was to be able to get new pieces of information, here too, this is what we're going to want to do with our Bayesian network. In the context of knowledge, we talked about the problem of inference. Given things that I know to be true, can I draw conclusions, make deductions about other facts about the world that I also know to be true? And what we're going to do now is apply the same sort of idea to probability. Using information about which I have some knowledge, whether some evidence or some probabilities, can I figure out not other variables for certain, but can I figure out the probabilities of other variables taking on particular values? And so here we introduce the problem of inference in a probabilistic setting, in a case where variables might not necessarily be true for sure, but they might be random variables that take on different values with some probability. So how do we formally define what exactly this inference problem actually is? Well, the inference problem has a couple of parts to it. We have some query, some variable x that we want to compute the distribution for. Maybe I want the probability that I miss my train, or I want the probability that there is track maintenance, something that I want information about. And then I have some evidence variables. Maybe it's just one piece of evidence, maybe it's multiple pieces of evidence, but I've observed certain variables for some sort of event. So for example, I might have observed that it is raining. This is evidence that I have. I know that there is light rain, or I know that there is heavy rain. And that is evidence I have. And using that evidence, I want to know what is the probability that my train is delayed, for example. And that is a query that I might want to ask based on this evidence. So I have a query, some variable, evidence, which are some other variables that I have observed inside of my Bayesian network. And of course, that does leave some hidden variables. Why? These are variables that are not evidence variables and not query variables. So you might imagine in the case where I know whether or not it's raining, and I want to know whether my train is going to be delayed or not. The hidden variable, the thing I don't have access to, is something like, is there maintenance on the track? Or am I going to make or not make my appointment, for example? These are variables that I don't have access to. They're hidden because they're not things I observed, and they're also not the query, the thing that I'm asking. And so ultimately what we want to calculate is I want to know the probability distribution of x given E, the event that I observe. So given that I observe some event, I observe that it is raining, I would like to know what is the distribution over the possible values of the train random variable. Is it on time? Is it delayed? What's the likelihood that's going to be there? And it turns out we can do this calculation just using a lot of the probability rules that we've already seen in action. And ultimately, we're going to take a look at the math on a little bit of a high level, at an abstract level. But ultimately, we can allow computers and programming libraries that already exist to begin to do some of this math for us. But it's good to get a general sense for what's actually happening when this inference process takes place. Let's imagine, for example, that I want to compute the probability distribution of the appointment random variable given some evidence, given that I know that there was light rain and no track maintenance. So there's my evidence, these two variables that I observe the values of. I observe the value of rain. I know there's light rain. And I know that there is no track maintenance going on today. And what I care about knowing, my query, is this random variable, appointment. I want to know the distribution of this random variable appointment, like what is the chance that I'm able to attend my appointment, what is the chance that I miss my appointment, given this evidence. And the hidden variable, the information that I don't have access to, is this variable train. This is information that is not part of the evidence that I see, not something that I observe, but it is also not the query that I'm asking for. And so what might this inference procedure look like? Well, if you recall back from when we were defining conditional probability and doing math with conditional probabilities, we know that a conditional probability is proportional to the joint probability. And we remember this by recalling that the probability of A given B is just some constant factor alpha multiplied by the probability of A and B. That constant factor alpha turns out to be like dividing over the probability of B. But the important thing is that it's just some constant multiplied by the joint distribution, the probability that all of these individual things happen. So in this case, I can take the probability of the appointment random variable given light rain and no track maintenance, and say that is just going to be proportional, some constant alpha, multiplied by the joint probability, the probability of a particular value for the appointment random variable and light rain and no track maintenance. Well, all right, how do I calculate this, probability of appointment and light rain and no track maintenance, when what I really care about is knowing, like, I need all four of these values to be able to calculate a joint distribution across everything, because in a particular appointment depends upon the value of train. Well, in order to do that, here I can begin to use that marginalization trick, that there are only two ways I can get any configuration of an appointment, light rain, and no track maintenance. Either this particular setting of variables happens and the train is on time, or this particular setting of variables happens and the train is delayed. Those are two possible cases that I would want to consider. And if I add those two cases up, well, then I get the result just by adding up all of the possibilities for the hidden variable, or variables if there are multiple. But since there's only one hidden variable here, train, all I need to do is iterate over all the possible values for that hidden variable train and add up their probabilities. So this probability expression here becomes probability distribution over appointment, light, no rain, and train is on time, and the probability distribution over the appointment, light, rain, no track maintenance, and that the train is delayed, for example. So I take both of the possible values for train, go ahead and add them up. These are just joint probabilities that we saw earlier how to calculate just by going parent, 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 and calculating those probabilities and multiplying them together. And then you'll need to normalize them at the end, speaking at a high level, to make sure that everything adds up to the number 1. So the formula for how you do this in a process known as inference by enumeration looks a little bit complicated, but ultimately it looks like this. And let's now try to distill what it is that all of these symbols actually mean. Let's start here. What I care about knowing is the probability of x, my query variable, given some sort of evidence. What do I know about conditional probabilities? Well, a conditional probability is proportional to the joint probability. So it's some alpha, some normalizing constant, multiplied by this joint probability of x and evidence. And how do I calculate that? Well, to do that, I'm going to marginalize over all of the hidden variables, all the variables that I don't directly observe the values for. I'm basically going to iterate over all of the possibilities that it could happen and just sum them all up. And so I can translate this into a sum over all y, which ranges over all the possible hidden variables and the values that they could take on, and adds up all of those possible individual probabilities. And that is going to allow me to do this process of inference by enumeration. Now, ultimately, it's pretty annoying if we as humans have to do all of this math for ourselves, but turns out this is where computers and AI can be particularly helpful, that we can program a computer to understand a Bayesian network, to be able to understand these inference procedures, and to be able to do these calculations. And using the information you've seen here, you could implement a Bayesian network from scratch yourself, but turns out there are a lot of libraries, especially written in Python, that allow us to make it easier to do this sort of probabilistic inference, to be able to take a Bayesian network and do these sorts of calculations, so that you don't need to know and understand all of the underlying math, though it's helpful to have a general sense for how it works, but you just need to be able to describe the structure of the network and make queries in order to be able to produce the result. And so let's take a look at an example of that right now. It turns out that there are a lot of possible libraries that exist in Python for doing this sort of inference. It doesn't matter too much which specific library you use. They all behave in fairly similar ways. But the library I'm going to use here is one known as Pomegranate. And here inside of model.py, I have defined a Bayesian network, just using the structure and the syntax that the Pomegranate library expects. And what I'm effectively doing is just in Python creating nodes to represent each of the nodes of the Bayesian network that you saw me describe a moment ago. So here on line 4, after I've imported Pomegranate, I'm defining a variable called rain that is going to represent a node inside of my Bayesian network. It's going to be a node that follows this distribution, where there are 3 possible values, none for no rain, light for light rain, heavy for heavy rain. And these are the probabilities of each of those taking place. 0.7 is the likelihood of no rain, 0.2 for light rain, 0.1 for heavy rain. Then after that, we go to the next variable, the variable for track maintenance, for example, which is dependent upon that rain variable. And this, instead of being an unconditional distribution, is a conditional distribution, as indicated by a conditional probability table here. And the idea is that I'm following, this is conditional on the distribution of rain. So if there is no rain, then the chance that there is yes track maintenance is 0.4. If there's no rain, the chance that there's no track maintenance is 0.6. Likewise, for light rain, I have a distribution. For heavy rain, I have a distribution as well. But I'm effectively encoding the same information you saw represented graphically a moment ago. But I'm telling this Python program that the maintenance node obeys this particular conditional probability distribution. And we do the same thing for the other random variables as well. Train was a node inside my distribution that was a conditional probability table with 2 parents. It was dependent not only on rain, but also on track maintenance. And so here I'm saying something like, given that there is no rain and yes, track maintenance, the probability that my train is on time is 0.8, and the probability that it's delayed is 0.2. And likewise, I can do the same thing for all of the other possible values of the parents of the train node inside of my Bayesian network by saying, for all of those possible values, here is the distribution that the train node should follow. And I do the same thing for an appointment based on the distribution of the variable train. Then at the end, what I do is actually construct this network by describing what the states of the network are and by adding edges between the dependent nodes. So I create a new Bayesian network, add states to it, one for rain, one for maintenance, one for the train, one for the appointment. And then I add edges connecting the related pieces. Rain has an arrow to maintenance because rain influences track maintenance. Rain also influences the train. Maintenance also influences the train. And train influences whether I make it to my appointment. And bake just finalizes the model and does some additional computation. So the specific syntax of this is not really the important part. Pomegranate just happens to be one of several different libraries that can all be used for similar purposes. And you could describe and define a library for yourself that implemented similar things. But the key idea here is that someone can design a library for a general Bayesian network that has nodes that are based upon its parents. And then all a programmer needs to do using one of those libraries is to define what those nodes and what those probability distributions are. And we can begin to do some interesting logic based on it. So let's try doing that like conditional or joint probability calculation that we saw us do by hand before by going into likelihood.py, where here I'm importing the model that I just defined a moment ago. And here I'd just like to calculate model.probability, which calculates the probability for a given observation. And I'd like to calculate the probability of no rain, no track maintenance, my train is on time, and I'm able to attend the meeting. So sort of the optimal scenario, that there's no rain and no maintenance on the track, my train is on time, and I'm able to attend the meeting. What is the probability that all of that actually happens? And I can calculate that using the library and just print out its probability. And so I'll go ahead and run Python of likelihood.py. And I see that, OK, the probability is about 0.34. So about a third of the time, everything goes right for me in this case. No rain, no track maintenance, train is on time, and I'm able to attend the meeting. But I could experiment with this, try and calculate other probabilities as well. What's the probability that everything goes right up until the train, but I still miss my meeting? So no rain, no track maintenance, train is on time, but I missed the appointment. Let's calculate that probability. And all right, that has a probability of about 0.04. So about 4% of the time, the train will be on time, there won't be any rain, no track maintenance, and yet I'll still miss the meeting. And so this is really just an implementation of the calculation of the joint probabilities that we did before. What this library is likely doing is first figuring out the probability of no rain, then figuring out the probability of no track maintenance given no rain, then the probability that my train is on time given both of these values, and then the probability that I miss my appointment given that I know that the train was on time. So this, again, is the calculation of that joint probability. And turns out we can also begin to have our computer solve inference problems as well, to begin to infer, based on information, evidence that we see, what is the likelihood of other variables also being true. So let's go into inference.py, for example, where here I'm again importing that exact same model from before, importing all the nodes and all the edges and the probability distribution that is encoded there as well. And now there's a function for doing some sort of prediction. And here, into this model, I pass in the evidence that I observe. So here, I've encoded into this Python program the evidence that I have observed. I have observed the fact that the train is delayed. And that is the value for one of the 4 random variables inside of this Bayesian network. And using that information, I would like to be able to draw inspiration and figure out inferences about the values of the other random variables that are inside of my Bayesian network. I would like to make predictions about everything else. So all of the actual computational logic is happening in just these 3 lines, where I'm making this call to this prediction. Down below, I'm just iterating over all of the states and all the predictions and just printing them out so that we can visually see what the results are. But let's find out, given the train is delayed, what can I predict about the values of the other random variables? Let's go ahead and run Python inference.py. I run that. And all right, here is the result that I get. Given the fact that I know that the train is delayed, this is evidence that I have observed, well, given that there is a 45% chance or a 46% chance that there was no rain, a 31% chance there was light rain, a 23% chance there was heavy rain, I can see a probability distribution over track maintenance and a probability distribution over whether I'm able to attend or miss my appointment. Now, we know that whether I attend or miss the appointment, that is only dependent upon the train being delayed or not delayed. It shouldn't depend on anything else. So let's imagine, for example, that I knew that there was heavy rain. That shouldn't affect the distribution for making the appointment. And indeed, if I go up here and add some evidence, say that I know that the value of rain is heavy, that is evidence that I now have access to. I now have two pieces of evidence. I know that the rain is heavy, and I know that my train is delayed. I can calculate the probability by running this inference procedure again and seeing the result. I know that the rain is heavy. I know my train is delayed. The probability distribution for track maintenance changed. Given that I know that there's heavy rain, now it's more likely that there's no track maintenance, 88% as opposed to 64% from here before. And now, what is the probability that I make the appointment? Well, that's the same as before. It's still going to be attend the appointment with probability 0.6, miss the appointment with probability 0.4, because it was only dependent upon whether or not my train was on time or delayed. And so this here is implementing that idea of that inference algorithm to be able to figure out, based on the evidence that I have, what can we infer about the values of the other variables that exist as well. So inference by enumeration is one way of doing this inference procedure, just looping over all of the values the hidden variables could take on and figuring out what the probability is. Now, it turns out this is not particularly efficient, and there are definitely optimizations you can make by avoiding repeated work if you're calculating the same sort of probability multiple times. There are ways of optimizing the program to avoid having to recalculate the same probabilities again and again. But even then, as the number of variables get large, as the number of possible values those variables could take on get large, we're going to start to have to do a lot of computation, a lot of calculation to be able to do this inference. And at that point, it might start to get unreasonable in terms of the amount of time that it would take to be able to do this sort of exact inference. And it's for that reason that oftentimes when it comes towards probability and things we're not entirely sure about, we don't always care about doing exact inference and knowing exactly what the probability is. But if we can approximate the inference procedure, do some sort of approximate inference, that can be pretty good as well. That if I don't know the exact probability, but I have a general sense for the probability, that I can get increasingly accurate with more time, that's probably pretty good, especially if I can get that to happen even faster. So how could I do approximate inference inside of a Bayesian network? Well, one method is through a procedure known as sampling. In the process of sampling, I'm going to take a sample of all of the variables inside of this Bayesian network here. And how am I going to sample? Well, I'm going to sample one of the values from each of these nodes according to their probability distribution. So how might I take a sample of all these nodes? Well, I'll start at the root. I'll start with rain. Here's the distribution for rain. And I'll go ahead and, using a random number generator or something like it, randomly pick one of these three values. I'll pick none with probability 0.7, light with probability 0.2, and heavy with probability 0.1. So I'll randomly just pick one of them according to that distribution. And maybe in this case, I pick none, for example. Then I do the same thing for the other variable. Maintenance also has a probability distribution. And I'm going to sample. Now, there are three probability distributions here, but I'm only going to sample from this first row here because I've observed already in my sample that the value of rain is none. So given that rain is none, I'm going to sample from this distribution to say, all right, what should the value of maintenance be? And in this case, maintenance is going to be, let's just say yes, which happens 40% of the time in the event that there is no rain, for example. And we'll sample all of the rest of the nodes in this way as well. That I want to sample from the train distribution, and I'll sample from this first row here, where there is no rain, but there is track maintenance. And I'll sample 80% of the time. I'll say the train is on time. 20% of the time, I'll say the train is delayed. And finally, we'll do the same thing for whether I make it to my appointment or not. Did I attend or miss the appointment? We'll sample based on this distribution and maybe say that in this case, I attend the appointment, which happens 90% of the time when the train is actually on time. So by going through these nodes, I can very quickly just do some sampling and get a sample of the possible values that could come up from going through this entire Bayesian network according to those probability distributions. And where this becomes powerful is if I do this not once, but I do this thousands or tens of thousands of times and generate a whole bunch of samples all using this distribution. I get different samples, maybe some of them are the same, but I get a value for each of the possible variables that could come up. And so then if I'm ever faced with a question like, what is the probability that the train is on time? You could do an exact inference procedure. This is no different than the inference problem we had before, where I could just marginalize, look at all the possible other values of the variables, and do the computation of inference by enumeration to find out this probability exactly. But I could also, if I don't care about the exact probability, just sample it, approximate it to get close. And this is a powerful tool in AI where we don't need to be right 100% of the time, or we don't need to be exactly right. If we just need to be right with some probability, we can often do so more effectively, more efficiently. And so if here now are all of those possible samples, I'll sort of highlight the ones where the train is on time. I'm ignoring the ones where the train is delayed. And in this case, there's like 6 out of 8 of the samples have the train as arriving on time. And so maybe in this case, I can say that in 6 out of 8 cases, that's the likelihood that the train is on time. And with 8 samples, that might not be a great prediction. But if I had thousands upon thousands of samples, then this could be a much better inference procedure to be able to do these sorts of calculations. So this is a direct sampling method to just do a bunch of samples and then figure out what the probability of some event is. Now, this from before was an unconditional probability. What is the probability that the train is on time? And I did that by looking at all the samples and figuring out, all right, here are the ones where the train is on time. But sometimes what I'll want to calculate is not an unconditional probability, but rather a conditional probability. Something like, what is the probability that there is light rain given that the train is on time? Something to that effect. And to do that kind of calculation, well, what I might do is, here are all the samples that I have, and I want to calculate a probability distribution given that I know that the train is on time. So to be able to do that, I can kind of look at the 2 cases where the train was delayed and ignore or reject them, sort of exclude them from the possible samples that I'm considering. And now I want to look at these remaining cases where the train is on time. Here are the cases where there's light rain. And now I say, OK, these are 2 out of the 6 possible cases. That can give me an approximation for the probability of light rain, given the fact that I know the train was on time. And I did that in almost exactly the same way, just by adding an additional step, by saying that, all right, when I take each sample, let me reject all of the samples that don't match my evidence, and only consider the samples that do match what it is that I have in my evidence that I want to make some sort of calculation about. And it turns out, using the libraries that we've had for Bayesian networks, we can begin to implement this same sort of idea, like implement rejection sampling, which is what this method is called, to be able to figure out some probability, not via direct inference, but instead by sampling. So what I have here is a program called sample.py, imports the exact same model. And what I define first is a program to generate a sample. And the way I generate a sample is just by looping over all of the states. The states need to be in some sort of order to make sure I'm looping in the correct order. But effectively, if it is a conditional distribution, I'm going to sample based on the parents. And otherwise, I'm just going to directly sample the variable, like rain, which has no parents. It's just an unconditional distribution, and keep track of all those parent samples and return the final sample. The exact syntax of this, again, not particularly important. It just happens to be part of the implementation details of this particular library. The interesting logic is down below. Now that I have the ability to generate a sample, if I want to know the distribution of the appointment random variable, given that the train is delayed, well, then I can begin to do calculations like this. Let me take 10,000 samples and assemble all my results in this list called data. I'll go ahead and loop n times, in this case 10,000 times. I'll generate a sample. And I want to know the distribution of appointment given that the train is delayed. So according to rejection sampling, I'm only going to consider samples where the train is delayed. If the train's not delayed, I'm not going to consider those values at all. So I'm going to say, all right, if I take the sample, look at the value of the train random variable. If the train is delayed, well, let me go ahead and add to my data that I'm collecting the value of the appointment random variable that it took on in this particular sample. So I'm only considering the samples where the train is delayed, and for each of those samples, considering what the value of appointment is. And then at the end, I'm using a Python class called counter, which quickly counts up all the values inside of a data set. So I can take this list of data and figure out how many times was my appointment made and how many times was my appointment missed. And so this here, with just a couple lines of code, is an implementation of rejection sampling. And I can run it by going ahead and running python sample.py. And when I do that, here's the result I get. This is the result of the counter. 1,251 times I was able to attend the meeting, and 856 times I was able to miss the meeting. And you can imagine by doing more and more samples, I'll be able to get a better and better, more accurate result. And this is a randomized process. It's going to be an approximation of the probability. If I run it a different time, you'll notice the numbers are similar, 12, 72, and 905, but they're not identical because there's some randomization, some likelihood that things might be higher or lower. And so this is why we generally want to try and use more samples so that we can have a greater amount of confidence in our result, be more sure about the result that we're getting of whether or not it accurately reflects or represents the actual underlying probabilities that are inherent inside of this distribution. And so this then was an instance of rejection sampling. And it turns out there are a number of other sampling methods that you could use to begin to try to sample. One problem that rejection sampling has is that if the evidence you're looking for is a fairly unlikely event, well, you're going to be rejecting a lot of samples. Like if I'm looking for the probability of x given some evidence E, if E is very unlikely to occur, like occurs maybe 1 every 1,000 times, then I'm only going to be considering 1 out of every 1,000 samples that I do, which is a pretty inefficient method for trying to do this sort of calculation. I'm throwing away a lot of samples, and it takes computational effort to be able to generate those samples, so I'd like to not have to do something like that. So there are other sampling methods that can try and address this. One such sampling method is called likelihood weighting. In likelihood weighting, we follow a slightly different procedure, and the goal is to avoid needing to throw out samples that didn't match the evidence. And so what we'll do is we'll start by fixing the values for the evidence variables. Rather than sample everything, we're going to fix the values of the evidence variables and not sample those. Then we're going to sample all the other non-evidence variables in the same way, just using the Bayesian network, looking at the probability distributions, sampling all the non-evidence variables. But then what we need to do is weight each sample by its likelihood, right? If our evidence is really unlikely, we want to make sure that we've taken into account how likely was the evidence to actually show up in the sample. If I have a sample where the evidence was much more likely to show up than another sample, then I want to weight the more likely one higher. So we're going to weight each sample by its likelihood, where likelihood is just defined as the probability of all of the evidence. Given all the evidence we have, what is the probability that it would happen in that particular sample? So before, all of our samples were weighted equally. They all had a weight of 1 when we were calculating like the overall average. In this case, we're going to weight each sample, multiply each sample by its likelihood in order to get the more accurate distribution. So what would this look like? Well, if I ask the same question, what is the probability of light rain given that the train is on time? When I do the sampling procedure and start by trying to sample, I'm going to start by fixing the evidence variable. I'm already going to have in my sample the train is on time. That way, I don't have to throw out anything. I'm only sampling the things where I know the value of the variables that are my evidence are what I expect them to be. So I'll go ahead and sample from rain, and maybe this time I sample light rain instead of no rain. Then I'll sample from track maintenance and say maybe, yes, there's track maintenance. Then for train, well, I've already fixed it in place. Train was an evidence variable, so I'm not going to bother sampling again. I'll just go ahead and move on. I'll move on to appointment and go ahead and sample from appointment as well. So now I've generated a sample. I've generated a sample by fixing this evidence variable and sampling the other 3. And the last step is now weighting this sample. Like, how much weight should it have? And the weight is based on, like, how probable is it that the train was actually on time, this evidence actually happened, given the values of these other variables, light rain, and the fact that, yes, there was track maintenance. Well, to do that, I can just go back to the train variable and say, all right, if there was light rain and track maintenance, the likelihood of my evidence, the likelihood that my train was on time, is 0.6. And so this train, this particular sample, would have a weight of 0.6. And I could repeat the sampling procedure again and again. Each time every sample would be given a weight according to the probability of the evidence that I see associated with it. And there are other sampling methods that exist as well, but all of them are designed to try and get at the same idea, to approximate the inference procedure of figuring out the value of a variable. So we've now dealt with probability as it pertains to particular variables that have these discrete values. But what we haven't really considered is how values might change over time. That we've considered something like a variable for rain, where rain can take on values of none, or light rain, or heavy rain. But in practice, usually when we consider values for variables like rain, we like to consider it for over time, how do the values of these variables change? What do we do with when we're dealing with uncertainty over a period of time, which can come up in the context of weather, for example. If I have sunny days and I have rainy days, and I'd like to know not just like what is the probability that it's raining now, but what is the probability that it rains tomorrow, or the day after that, or the day after that? And so to do this, we're going to introduce a slightly different kind of model. But here we're going to have a random variable, not just one for the weather, but for every possible time step. And you can define time step however you like. A simple way is just to use days as your time step. And so we can define a variable called x sub t, which is going to be the weather at time t. So x sub 0 might be the weather on day 0. X sub 1 might be the weather on day 1, so on and so forth. X sub 2 is the weather on day 2. But as you can imagine, if we start to do this over longer and longer periods of time, there's an incredible amount of data that might go into this. If you're keeping track of data about the weather for a year, now suddenly you might be trying to predict the weather tomorrow, given 365 days of previous pieces of evidence. And that's a lot of evidence to have to deal with and manipulate and calculate. Probably nobody knows what the exact conditional probability distribution is for all of those combinations of variables. And so when we're trying to do this inference inside of a computer, when we're trying to reasonably do this sort of analysis, it's helpful to make some simplifying assumptions, some assumptions about the problem that we can just assume are true to make our lives a little bit easier. Even if they're not totally accurate assumptions, if they're close to accurate or approximate, they're usually pretty good. And the assumption we're going to make is called the Markov assumption, which is the assumption that the current state depends only on a finite fixed number of previous states. So the current day's weather depends not on all the previous day's weather for all of history, but the current day's weather I can predict just based on yesterday's weather, or just based on the last 2 days' weather, or the last 3 days' weather. But oftentimes we're going to deal with like just the one previous state helps to predict this current state. And by putting a whole bunch of these random variables together using this Markov assumption, we can create what's called a Markov chain, where a Markov chain is just some sequence of random variables where each of the variables' distribution follows that Markov assumption. And so we'll do an example of this where the Markov assumption is I can predict the weather. Is it sunny or rainy? And we'll just consider those two possibilities for now, even though there are other types of weather. But I can predict each day's weather just on the prior day's weather. Using today's weather, I can come up with a probability distribution for tomorrow's weather. And here's what this weather might look like. It's formatted in terms of a matrix, as you might describe it, as sort of rows and columns of values, where on the left-hand side, I have today's weather, represented by the variable x sub t. And over here in the columns, I have tomorrow's weather, represented by the variable x sub t plus 1, t plus 1 days weather instead. And what this matrix is saying is if today is sunny, well then, it's more likely than not that tomorrow is also sunny. Oftentimes the weather stays consistent for multiple days in a row. And for example, let's say that if today is sunny, our model says that tomorrow, with probability 0.8, it will also be sunny. And with probability 0.2, it will be raining. And likewise, if today is raining, then it's more likely than not that tomorrow is also raining. With probability 0.7, it'll be raining. With probability 0.3, it will be sunny. So this matrix, this description of how it is we transition from one state to the next state, is what we're going to call the transition model. And using the transition model, you can begin to construct this Markov chain by just predicting, given today's weather, what's the likelihood of tomorrow's weather happening? And you can imagine doing a similar sampling procedure where you take this information, you sample what tomorrow's weather is going to be. Using that, you sample the next day's weather. And the result of that is you can form this Markov chain of like x0, time day 0 is sunny, the next day is sunny, maybe the next day it changes to raining, then raining, then raining. And the pattern that this Markov chain follows, given the distribution that we had access to, this transition model here, is that when it's sunny, it tends to stay sunny for a little while. The next couple days tend to be sunny too. And when it's raining, it tends to be raining as well. And so you get a Markov chain that looks like this, and you can do analysis on this. You can say, given that today is raining, what is the probability that tomorrow is raining? Or you can begin to ask probability questions like, what is the probability of this sequence of 5 values, sun, sun, rain, 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 and answer those sorts of questions too. And it turns out there are, again, many Python libraries for interacting with models like this of probabilities that have distributions and random variables that are based on previous variables according to this Markov assumption. And Pomegranate 2 has ways of dealing with these sorts of variables. So I'll go ahead and go into the Markov, I'll go ahead and go into the chain directory where I have some information about Markov chains. And here I've defined a file called model.py, where I've defined, in a very similar syntax, And again, the exact syntax doesn't matter so much as the idea that I'm encoding this information into a Python program so that the program has access to these distributions. I've here defined some starting distribution. So every Markov model begins at some point in time, and I need to give it some starting distribution. And so we'll just say, you know, at the start, you can pick 50-50 between sunny and rainy. We'll say it's sunny 50% of the time, rainy 50% of the time. And then down below, I've here defined the transition model, how it is that I transition from one day to the next. And here I've encoded that exact same matrix from before, that if it was sunny today, then with probability 0.8, it will be sunny tomorrow. And it'll be rainy tomorrow with probability 0.2. And I likewise have another distribution for if it was raining today instead. And so that alone defines the Markov model. You can begin to answer questions using that model. But one thing I'll just do is sample from the Markov chain. And it turns out there's a method built into this Markov chain library that allows me to sample 50 states from the chain, basically just simulating like 50 instances of weather. And so let me go ahead and run this, Python model.py. And when I run it, what I get is that it's going to sample from this Markov chain 50 states, 50 days worth of weather that it's just going to randomly sample. And you can imagine sampling many times to be able to get more data, to be able to do more analysis. But here, for example, it's sunny 2 days in a row, rainy a whole bunch of days in a row before it changes back to sun. And so you get this model that follows the distribution that we originally described, that follows the distribution of sunny days tend to lead to more sunny days, rainy days tend to lead to more rainy days. And that then is a Markov model. And Markov models rely on us knowing the values of these individual states. I know that today is sunny or that today is rainy. And using that information, I can draw some sort of inference about what tomorrow is going to be like. But in practice, this often isn't the case. It often isn't the case that I know for certain what the exact state of the world is. Oftentimes, the state of the world is exactly unknown, but I'm able to somehow sense some information about that state, that a robot or an AI doesn't have exact knowledge about the world around it, but it has some sort of sensor, whether that sensor is a camera or like sensors that detect distance or just a microphone that is sensing audio, for example. It is sensing data, and using that data is somehow related to the state of the world, even if it doesn't actually know, our AI doesn't know what the underlying true state of the world actually is. And for that, we need to get into the world of sensor models, the way of describing how it is that we translate what the hidden state, the underlying true state of the world is, with what the observation, what it is that the AI knows or the AI has access to, actually is. And so, for example, a hidden state might be a robot's position. If a robot is exploring new uncharted territory, the robot likely doesn't know exactly where it is, but it does have an observation. It has robot sensor data where it can sense how far away are possible obstacles around it. And using that information, using the observed information that it has, it can infer something about the hidden state. Because what the true hidden state is influences those observations. Whatever the robot's true position is affects or has some effect upon what the sensor data the robot is able to collect is, even if the robot doesn't actually know for certain what its true position is. Likewise, if you think about a voice recognition or a speech recognition program that listens to you and is able to respond to you, something like Alexa or what Apple and Google are doing with their voice recognition as well, that you might imagine that the hidden state, the underlying state, is what words are actually spoken. The true nature of the world contains you saying a particular sequence of words, but your phone or your smart home device doesn't know for sure exactly what words you said. The only observation that the AI has access to is like some audio waveforms. And those audio waveforms are, of course, dependent upon this hidden state. And you can infer, based on those audio waveforms, what the words spoken likely were. But you might not know with 100% certainty what that hidden state actually is. And it might be a task to try and predict, given this observation, given these audio waveforms, can you figure out what the actual words spoken are? Likewise, you might imagine on a website, true user engagement might be information you don't directly have access to, but you can observe data, like website or app analytics, about how often was this button clicked, or how often are people interacting with a page in a particular way. And you can use that to infer things about your users as well. So this type of problem comes up all the time when we're dealing with AI and trying to infer things about the world. That often AI doesn't really know the hidden true state of the world. All the AI has access to is some observation that is related to the hidden true state, but it's not direct. There might be some noise there. The audio waveform might have some additional noise that might be difficult to parse. The sensor data might not be exactly correct. There's some noise that might not allow you to conclude with certainty what the hidden state is, but can allow you to infer what it might be. And so the simple example we'll take a look at here is imagining the hidden state as the weather, whether it's sunny or rainy or not. And imagine you are programming an AI inside of a building that maybe has access to just a camera to inside the building. And all you have access to is an observation as to whether or not employees are bringing an umbrella into the building or not. You can detect whether it's an umbrella or not. And so you might have an observation as to whether or not an umbrella is brought into the building or not. And using that information, you want to predict whether it's sunny or rainy, even if you don't know what the underlying weather is. So the underlying weather might be sunny or rainy. And if it's raining, obviously people are more likely to bring an umbrella. And so whether or not people bring an umbrella, your observation tells you something about the hidden state. And of course, this is a bit of a contrived example, but the idea here is to think about this more broadly in terms of more generally, anytime you observe something, it having to do with some underlying hidden state. And so to try and model this type of idea, where we have these hidden states and observations, rather than just use a Markov model, which has state, 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 each of which is connected by that transition matrix that we described before, we're going to use what we call a hidden Markov model. Very similar to a Markov model, but this is going to allow us to model a system that has hidden states that we don't directly observe, along with some observed event that we do actually see. And so in addition to that transition model that we still need of saying, given the underlying state of the world, if it's sunny or rainy, what's the probability of tomorrow's weather? We also need another model that, given some state, is going to give us an observation of like green, yes, someone brings an umbrella into the office, or red, no, nobody brings umbrellas into the office. And so the observation might be that if it's sunny, then odds are nobody's going to bring an umbrella to the office. But maybe some people are just being cautious, and they do bring an umbrella to the office anyways. And if it's raining, then with much higher probability, then people are going to bring umbrellas into the office. But maybe if the rain was unexpected, people didn't bring an umbrella. And so it might have some other probability as well. So using the observations, you can begin to predict with reasonable likelihood what the underlying state is, even if you don't actually get to observe the underlying state, if you don't get to see what the hidden state is actually equal to. This here we'll often call the sensor model. It's also often called the emission probabilities, because the state, the underlying state, emits some sort of emission that you then observe. And so that can be another way of describing that same idea. And the sensor Markov assumption that we're going to use is this assumption that the evidence variable, the thing we observe, the emission that gets produced, depends only on the corresponding state, meaning I can predict whether or not people will bring umbrellas or not, entirely dependent just on whether it is sunny or rainy today. Of course, again, this assumption might not hold in practice, that in practice it might depend whether or not people bring umbrellas, might depend not just on today's weather, but also on yesterday's weather and the day before. But for simplification purposes, it can be helpful to apply this sort of assumption just to allow us to be able to reason about these probabilities a little more easily. And if we're able to approximate it, we can still often get a very good answer. And so what these hidden Markov models end up looking like is a little something like this, where now, rather than just have one chain of states like sun, sun, rain, 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 we instead have this upper level, which is the underlying state of the world. Is it sunny or is it rainy? And those are connected by that transition matrix we described before. But each of these states produces an emission, produces an observation that I see, that on this day it was sunny and people didn't bring umbrellas. And on this day it was sunny, but people did bring umbrellas. And on this day it was raining and people did bring umbrellas, and so on and so forth. And so each of these underlying states, represented by x sub t for x sub 1, 0, 1, 2, so on and so forth, produces some sort of observation or emission, which is what the E stands for, E sub 0, E sub 1, E sub 2, so on and so forth. And so this, too, is a way of trying to represent this idea. And what you want to think about is that these underlying states are the true nature of the world, the robot's position as it moves over time, and that produces some sort of sensor data that might be observed, or what people are actually saying, and using the emission data of what audio waveforms do you detect in order to process that data and try and figure it out. And there are a number of possible tasks that you might want to do given this kind of information. And one of the simplest is trying to infer something about the future or the past, or about these sort of hidden states that might exist. And so the tasks that you'll often see, and we're not going to go into the mathematics of these tasks, but they're all based on the same idea of conditional probabilities and using the probability distributions we have to draw these sorts of conclusions. One task is called filtering, which is given observations from the start until now, calculate the distribution for the current state. Meaning, given information about from the beginning of time until now, on which days do people bring an umbrella or not bring an umbrella, can I calculate the probability of the current state, that today, is it sunny or is it raining? Another task that might be possible is prediction, which is looking towards the future. Given observations about people bringing umbrellas from the beginning of when we started counting time until now, can I figure out the distribution that tomorrow, is it sunny or is it raining? And you can also go backwards as well via smoothing, where I can say, given observations from start until now, calculate the distributions for some past state. Like I know that today people brought umbrellas, and tomorrow people brought umbrellas. And so given 2 days worth of data of people bringing umbrellas, what's the probability that yesterday it was raining? And that I know that people brought umbrellas today, that might inform that decision as well. It might influence those probabilities. And there's also a most likely explanation task, in addition to other tasks that might exist as well, which is combining some of these, given observations from the start up until now, figuring out the most likely sequence of states. And this is what we're going to take a look at now, this idea that if I have all these observations, umbrella, no umbrella, umbrella, no umbrella, can I calculate the most likely states of sun, rain, and whatnot that actually represented the true weather that would produce these observations. And this is quite common when you're trying to do something like voice recognition, for example, that you have these emissions of these audio waveforms, and you would like to calculate, based on all of the observations that you have, what is the most likely sequence of actual words or syllables or sounds that the user actually made when they were speaking to this particular device, or other tasks that might come up in that context as well. And so we can try this out by going ahead and going into the HMM directory, HMM for Hidden Markov Model. And here, what I've done is I've defined a model where this model first defines my possible state, sun and rain, along with their emission probabilities, the observation model or the emission model, where here, given that I know that it's sunny, the probability that I see people bring an umbrella is 0.2. The probability of no umbrella is 0.8. And likewise, if it's raining, then people are more likely to bring an umbrella. Umbrella has probability 0.9. No umbrella has probability 0.1. So the actual underlying hidden states, those states are sun and rain. But the things that I observe, the observations that I can see, are either umbrella or no umbrella as the things that I observe as a result. So this then, I also need to add to it a transition matrix, same as before, saying that if today is sunny, then tomorrow is more likely to be sunny. And if today is rainy, then tomorrow is more likely to be raining. As with before, I give it some starting probabilities, saying at first, 50-50 chance for whether it's sunny or rainy. And then I can create the model based on that information. Again, the exact syntax of this is not so important, so much as it is the data that I am now encoding into a program, such that now I can begin to do some inference. So I can give my program, for example, a list of observations. Umbrella, umbrella, no umbrella, 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 so on and so forth, no umbrella, no umbrella. And I would like to calculate, I would like to figure out the most likely explanation for these observations. What is likely? Was it rain, rain? Is this rain? Or is it more likely that this was actually sunny, and then it switched back to it being rainy? And that's an interesting question. We might not be sure, because it might just be that it just so happened on this rainy day, people decided not to bring an umbrella. Or it could be that it switched from rainy to sunny back to rainy, which doesn't seem too likely, but it certainly could happen. And using the data we give to the hidden Markov model, our model can begin to predict these answers, can begin to figure it out. So we're going to go ahead and just predict these observations, and then for each of those predictions, go ahead and print out what the prediction is. And this library just so happens to have a function called predict that does this prediction process for me. So I'll run Python sequence.py, and the result I get is this. This is the prediction based on the observations of what all of those states are likely to be. And it's likely to be rain, then rain. In this case, it thinks that what most likely happened is that it was sunny for a day and then went back to being rainy. But in different situations, if it was rainy for longer maybe, or if the probabilities were slightly different, you might imagine that it's more likely that it was rainy all the way through, and it just so happened on one rainy day, people decided not to bring umbrellas. And so here too, Python libraries can begin to allow for this sort of inference procedure. And by taking what we know and by putting it in terms of these tasks that already exist, these general tasks that work with hidden Markov models, then any time we can take an idea and formulate it as a hidden Markov model, formulate it as something that has hidden states and observed emissions that result from those states, then we can take advantage of these algorithms that are known to exist for trying to do this sort of inference. So now we've seen a couple of ways that AI can begin to deal with uncertainty. We've taken a look at probability and how we can use probability to describe numerically things that are likely or more likely or less likely to happen than other events or other variables. And using that information, we can begin to construct these standard types of models, things like Bayesian networks and Markov chains and hidden Markov models that all allow us to be able to describe how particular events relate to other events or how the values of particular variables relate to other variables, not for certain, but with some sort of probability distribution. And by formulating things in terms of these models that already exist, we can take advantage of Python libraries that implement these sort of models already and allow us just to be able to use them to produce some sort of resulting effect. So all of this then allows our AI to begin to deal with these sort of uncertain problems so that our AI doesn't need to know things for certain, but can infer based on information it doesn't know. Next time, we'll take a look at additional types of problems that we can solve by taking advantage of AI-related algorithms even beyond the world of the types of problems we've already explored. We'll see you next time. OK, welcome back, everyone, to an introduction to artificial intelligence with Python. And now, so far, we've taken a look at a couple of different types of problems. We've seen classical search problems where we're trying to get from an initial state to a goal by figuring out some optimal path. We've taken a look at adversarial search, where we have a game-playing agent that is trying to make the best move. We've seen knowledge-based problems where we're trying to use logic and inference to be able to figure out and draw some additional conclusions. And we've seen some probabilistic models as well, where we might not have certain information about the world, but we want to use the knowledge about probabilities that we do have to be able to draw some conclusions. Today, we're going to turn our attention to another category of problems generally known as optimization problems, where optimization is really all about choosing the best option from a set of possible options. And we've already seen optimization in some contexts, like game playing, where we're trying to create an AI that chooses the best move out of a set of possible moves. But what we'll take a look at today is a category of types of problems and algorithms to solve them that can be used in order to deal with a broader range of potential optimization problems. And the first of the algorithms that we'll take a look at is known as local search. And local search differs from search algorithms we've seen before in the sense that the search algorithms we've looked at so far, which are things like breadth-first search or A-star search, for example, generally maintain a whole bunch of different paths that we're simultaneously exploring, and we're looking at a bunch of different paths at once, trying to find our way to the solution. On the other hand, in local search, this is going to be a search algorithm that's really just going to maintain a single node, looking at a single state. And we'll generally run this algorithm by maintaining that single node and then moving ourselves to one of the neighboring nodes throughout this search process. And this is generally useful in contexts not like these problems, which we've seen before, like a maze-solving situation where we're trying to find our way from the initial state to the goal by following some path. But local search is most applicable when we really don't care about the path at all, and all we care about is what the solution is. And in the case of solving a maze, the solution was always obvious. You could point to the solution. You know exactly what the goal is. And the real question is, what is the path to get there? But local search is going to come up in cases where figuring out exactly what the solution is, exactly what the goal looks like, is actually the heart of the challenge. And to give an example of one of these kinds of problems, we'll consider a scenario where we have two types of buildings, for example. We have houses and hospitals. And our goal might be, in a world that's formatted as this grid, where we have a whole bunch of houses, a house here, two houses over there, maybe we want to try and find a way to place two hospitals on this map. So maybe a hospital here and a hospital there. And the problem now is we want to place two hospitals on the map, but we want to do so with some sort of objective. And our objective in this case is to try and minimize the distance of any of the houses from a hospital. So you might imagine, all right, what's the distance from each of the houses to their nearest hospital? There are a number of ways we could calculate that distance. But one way is using a heuristic we've looked at before, which is the Manhattan distance, this idea of how many rows and columns would you have to move inside of this grid layout in order to get to a hospital, for example. And it turns out if you take each of these 4 houses and figure out, all right, how close are they to their nearest hospital, you get something like this, where this house is 3 away from a hospital, this house is 6 away, these 2 houses are each 4 away. And if you add all those numbers up together, you get a total cost of 17, for example. So for this particular configuration of hospitals, a hospital here and a hospital there, that state, we might say, has a cost of 17. And the goal of this problem now that we would like to apply a search algorithm to figure out is, can you solve this problem to find a way to minimize that cost, minimize the total amount? If you sum up all of the distances from all the houses to the nearest hospital, how can we minimize that final value? And if we think about this problem a little bit more abstractly, abstracting away from this specific problem and thinking more generally about problems like it, you can often formulate these problems by thinking about them as a state space landscape, as we'll soon call it. Here in this diagram of a state space landscape, each of these vertical bars represents a particular state that our world could be in. So for example, each of these vertical bars represents a particular configuration of 2 hospitals. And the height of this vertical bar is generally going to represent some function of that state, some value of that state. So maybe in this case, the height of the vertical bar represents what is the cost of this particular configuration of hospitals in terms of what is the sum total of all of the distances from all of the houses to their nearest hospital. And generally speaking, when we have a state space landscape, we want to do one of 2 things. We might be trying to maximize the value of this function, trying to find a global maximum, so to speak, of this state space landscape, a single state whose value is higher than all of the other states that we could possibly choose from. And generally, in this case, when we're trying to find a global maximum, we'll call the function that we're trying to optimize some objective function, some function that measures for any given state how good is that state, such that we can take any state, pass it into the objective function, and get a value for how good that state is. And ultimately, what our goal is to find one of these states that has the highest possible value for that objective function. An equivalent but reversed problem is the problem of finding a global minimum, some state that has a value after you pass it into this function that is lower than all of the other possible values that we might choose from. And generally speaking, when we're trying to find a global minimum, we call the function that we're calculating a cost function. Generally, each state has some sort of cost, whether that cost is a monetary cost or a time cost, or in the case of the houses and hospitals we've been looking at just now, a distance cost in terms of how far away each of the houses is from a hospital. And we're trying to minimize the cost, find the state that has the lowest possible value of that cost. So these are the general types of ideas that we might be trying to go for within a state space landscape, trying to find a global maximum or trying to find a global minimum. And how exactly do we do that? We'll recall that in local search, we generally operate this algorithm by maintaining just a single state, just some current state represented inside of some node, maybe inside of a data structure, where we're keeping track of where we are currently. And then ultimately what we're going to do is from that state, move to one of its neighbor states. So in this case, represented in this one-dimensional space by just the state immediately to the left or to the right of it. But for any different problem, you might define what it means for there to be a neighbor of a particular state. In the case of a hospitals, for example, that we were just looking at, a neighbor might be moving one hospital one space to the left or to the right or up or down, some state that is close to our current state, but slightly different, and as a result, might have a slightly different value in terms of its objective function or in terms of its cost function. So this is going to be our general strategy in local search, to be able to take a state, maintaining some current node, and move where we're looking at in this state space landscape in order to try to find a global maximum or a global minimum somehow. And perhaps the simplest of algorithms that we could use to implement this idea of local search is an algorithm known as hill climbing. And the basic idea of hill climbing is, let's say I'm trying to maximize the value of my state. I'm trying to figure out where the global maximum is. I'm going to start at a state. And generally, what hill climbing is going to do is it's going to consider the neighbors of that state. That from this state, all right, I could go left or I could go right. And this neighbor happens to be higher and this neighbor happens to be lower. And in hill climbing, if I'm trying to maximize the value, I'll generally pick the highest one I can. Between the state to the left and right of me, this one is higher. So I'll go ahead and move myself to consider that state instead. And then I'll repeat this process, continually looking at all of my neighbors and picking the highest neighbor, doing the same thing, looking at my neighbors, picking the highest of my neighbors, until I get to a point like right here, where I consider both of my neighbors, and both of my neighbors have a lower value than I do. This current state has a value that is higher than any of its neighbors. And at that point, the algorithm terminates, and I can say, all right, here I have now found the solution. And the same thing works in exactly the opposite way for trying to find a global minimum. But the algorithm is fundamentally the same. If I'm trying to find a global minimum and say my current state starts here, I'll continually look at my neighbors, pick the lowest value that I possibly can, until I eventually, hopefully, find that global minimum, a point at which, when I look at both of my neighbors, they each have a higher value, and I'm trying to minimize the total score or cost or value that I get as a result of calculating some sort of cost function. So we can formulate this graphical idea in terms of pseudocode. And the pseudocode for hill climbing might look like this. We define some function called hillclimb that takes as input the problem that we're trying to solve. And generally, we're going to start in some sort of initial state. So I'll start with a variable called current that is keeping track of my initial state, like an initial configuration of hospitals. And maybe some problems lend themselves to an initial state, some place where you begin. In other cases, maybe not, in which case we might just randomly generate some initial state, just by choosing 2 locations for hospitals at random, for example, and figuring out from there how we might be able to improve. But that initial state, we're going to store inside of current. And now here comes our loop, some repetitive process we're going to do again and again until the algorithm terminates. And what we're going to do is first say, let's figure out all of the neighbors of the current state. From my state, what are all of the neighboring states for some definition of what it means to be a neighbor? And I'll go ahead and choose the highest valued of all of those neighbors and save it inside of this variable called neighbor. So we'll keep track of the highest valued neighbor. This is in the case where I'm trying to maximize the value. In the case where I'm trying to minimize the value, you might imagine here you'll pick the neighbor with the lowest possible value. But these ideas are really fundamentally interchangeable. And it's possible in some cases there might be multiple neighbors that each have an equally high value or an equally low value in the minimizing case. And in that case, we can just choose randomly from among them. Just choose one of them and save it inside of this variable neighbor. And then the key question to ask is this neighbor better than my current state? And if the neighbor, the best neighbor that I was able to find, is not better than my current state, well, then the algorithm is over. And I'll just go ahead and return the current state. If none of my neighbors are better, then I may as well stay where I am, is the general logic of the hill climbing algorithm. But otherwise, if the neighbor is better, then I may as well move to that neighbor. So you might imagine setting current equal to neighbor, where the general idea is if I'm at a current state and I see a neighbor that is better than me, then I'll go ahead and move there. And then I'll repeat the process, continually moving to a better neighbor until I reach a point at which none of my neighbors are better than I am. And at that point, we'd say the algorithm can just terminate there. So let's take a look at a real example of this with these houses and hospitals. So we've seen now that if we put the hospitals in these 2 locations, that has a total cost of 17. And now we need to define, if we're going to implement this hill climbing algorithm, what it means to take this particular configuration of hospitals, this particular state, and get a neighbor of that state. And a simple definition of neighbor might be just, let's pick one of the hospitals and move it by 1 square, to the left or right or up or down, for example. And that would mean we have 6 possible neighbors from this particular configuration. We could take this hospital and move it to any of these 3 possible squares, or we take this hospital and move it to any of those 3 possible squares. And each of those would generate a neighbor. And what I might do is say, all right, here's the locations and the distances between each of the houses and their nearest hospital. Let me consider all of the neighbors and see if any of them can do better than a cost of 17. And it turns out there are a couple of ways that we could do that. And it doesn't matter if we randomly choose among all the ways that are the best. But one such possible way is by taking a look at this hospital here and considering the directions in which it might move. If we hold this hospital constant, if we take this hospital and move it 1 square up, for example, that doesn't really help us. It gets closer to the house up here, but it gets further away from the house down here. And it doesn't really change anything for the 2 houses along the left-hand side. But if we take this hospital on the right and move it 1 square down, it's the opposite problem. It gets further away from the house up above, and it gets closer to the house down below. The real idea, the goal should be to be able to take this hospital and move it 1 square to the left. By moving it 1 square to the left, we move it closer to both of these houses on the right without changing anything about the houses on the left. For them, this hospital is still the closer one, so they aren't affected. So we're able to improve the situation by picking a neighbor that results in a decrease in our total cost. And so we might do that, move ourselves from this current state to a neighbor by just taking that hospital and moving it. And at this point, there's not a whole lot that can be done with this hospital, but there's still other optimizations we can make, other neighbors we can move to that are going to have a better value. If we consider this hospital, for example, we might imagine that right now it's a bit far up, that both of these houses are a little bit lower. So we might be able to do better by taking this hospital and moving it one square down, moving it down so that now instead of a cost of 15, we're down to a cost of 13 for this particular configuration. And we can do even better by taking the hospital and moving it one square to the left. Now instead of a cost of 13, we have a cost of 11, because this house is 1 away from the hospital, this one is 4 away, this one is 3 away, and this one is also 3 away. So we've been able to do much better than that initial cost that we had using the initial configuration, just by taking every state and asking ourselves the question, can we do better by just making small incremental changes, moving to a neighbor, moving to a neighbor, and moving to a neighbor after that? And now at this point, we can potentially see that at this point the algorithm is going to terminate. There's actually no neighbor we can move to that is going to improve the situation, get us a cost that is less than 11. Because if we take this hospital and move it up or to the right, well, that's going to make it further away. If we take it and move it down, that doesn't really change the situation. It gets further away from this house but closer to that house. And likewise, the same story was true for this hospital. Any neighbor we move it to, up, left, down, or right, is either going to make it further away from the houses and increase the cost, or it's going to have no effect on the cost whatsoever. And so the question we might now ask is this the best we could do? Is this the best placement of the hospitals we could possibly have? And it turns out the answer is no, because there's a better way that we could place these hospitals. And in particular, there are a number of ways you could do this, but one of the ways is by taking this hospital here and moving it to this square, for example, moving it diagonally by 1 square, which was not part of our definition of neighbor. We could only move left, right, up, or down. But this is in fact better. It has a total cost of 9. It is now closer to both of these houses, and as a result, the total cost is less. But we weren't able to find it because in order to get there, we had to go through a state that actually wasn't any better than the current state that we had been on previously. And so this appears to be a limitation or a concern you might have as you go about trying to implement a hill climbing algorithm, is that it might not always give you the optimal solution. If we're trying to maximize the value of any particular state, we're trying to find the global maximum, a concern might be that we could get stuck at one of the local maxima, highlighted here in blue, where a local maxima is any state whose value is higher than any of its neighbors. If we ever find ourselves at one of these two states when we're trying to maximize the value of the state, we're not going to make any changes. We're not going to move left or right. We're not going to move left here, because those states are worse. But yet, we haven't found the global optimum. We haven't done as best as we could do. And likewise, in the case of the hospitals, what we're ultimately trying to do is find a global minimum, find a value that is lower than all of the others. But we have the potential to get stuck at one of the local minima, any of these states whose value is lower than all of its neighbors, but still not as low as the local minima. And so the takeaway here is that it's not always going to be the case that when we run this naive hill climbing algorithm, that we're always going to find the optimal solution. There are things that could go wrong. If we started here, for example, and tried to maximize our value as much as possible, we might move to the highest possible neighbor, move to the highest possible neighbor, move to the highest possible neighbor, and stop, and never realize that there's actually a better state way over there that we could have gone to instead. And other problems you might imagine, just by taking a look at this state space landscape, are these various different types of plateaus. Something like this flat local maximum here, where all 6 of these states each have the exact same value. And so in the case of the algorithm we showed before, none of the neighbors are better, so we might just get stuck at this flat local maximum. And even if you allowed yourself to move to one of the neighbors, it wouldn't be clear which neighbor you would ultimately move to, and you could get stuck here as well. And there's another one over here. This one is called a shoulder. It's not really a local maximum because there's still places where we can go higher, not a local minimum because we can go lower. So we can still make progress, but it's still this flat area where if you have a local search algorithm, there's potential to get lost here, unable to make some upward or downward progress depending on whether we're trying to maximize or minimize, and therefore another potential for us to be able to find a solution that might not actually be the optimal solution. And so because of this potential, the potential that hill climbing has to not always find us the optimal result, it turns out there are a number of different varieties and variations on the hill climbing algorithm that help to solve the problem better depending on the context. And depending on the specific type of problem, some of these variants might be more applicable than others. What we've taken a look at so far is a version of hill climbing generally called steepest ascent hill climbing, where the idea of steepest ascent hill climbing is we are going to choose the highest valued neighbor in the case where we're trying to maximize, or the lowest valued neighbor in cases where we're trying to minimize. But generally speaking, if I have 5 neighbors and they're all better than my current state, I will pick the best one of those 5. Now, sometimes that might work pretty well. It's sort of a greedy approach of trying to take the best operation at any particular time step. But it might not always work. There might be cases where actually I want to choose an option that is slightly better than me, but maybe not the best one, because that later on might lead to a better outcome ultimately. So there are other variants that we might consider of this basic hill climbing algorithm. One is known as stochastic hill climbing. And in this case, we choose randomly from all of our higher valued neighbors. So if I'm at my current state and there are 5 neighbors that are all better than I am, rather than choosing the best one, as steepest ascent would do, stochastic will just choose randomly from one of them, thinking that if it's better, then it's better, and maybe there's a potential to make forward progress, even if it is not locally the best option I could possibly choose. First choice hill climbing ends up just choosing the very first highest valued neighbor that it follows, behaving on a similar idea, rather than consider all of the neighbors. As soon as we find a neighbor that is better than our current state, we'll go ahead and move there. So maybe some efficiency improvements there, and maybe has the potential to find a solution that the other strategies weren't able to find. And with all of these variants, we still suffer from the same potential risk, this risk that we might end up at a local minimum or a local maximum. And we can reduce that risk by repeating the process multiple times. So one variant of hill climbing is random restart hill climbing, where the general idea is we'll conduct hill climbing multiple times. If we apply steepest ascent hill climbing, for example, we'll start at some random state, try and figure out how to solve the problem, and figure out what is the local maximum or local minimum we get to. And then we'll just randomly restart and try again. Choose a new starting configuration, try and figure out what the local maximum or minimum is, and do this some number of times. And then after we've done it some number of times, we can pick the best one out of all of the ones that we've taken a look at. So there's another option we have access to as well. And then, although I said that generally local search will usually just keep track of a single node and then move to one of its neighbors, there are variants of hill climbing that are known as local beam searches, where rather than keep track of just one current best state, we're keeping track of k highest valued neighbors, such that rather than starting at one random initial configuration, I might start with 3 or 4 or 5, randomly generate all the neighbors, and then pick like the 3 or 4 or 5 best of all of the neighbors that I find, and continually repeat this process, with the idea being that now I have more options that I'm considering, more ways that I could potentially navigate myself to the optimal solution that might exist for a particular problem. So let's now take a look at some actual code that can implement some of these kinds of ideas, something like steepest ascent hill climbing, for example, for trying to solve this hospital problem. So I'm going to go ahead and go into my hospitals directory, where I've actually set up the basic framework for solving this type of problem. I'll go ahead and go into hospitals.py, and we'll take a look at the code we've created here. I've defined a class that is going to represent the state space. So the space has a height and a width, and also some number of hospitals. So you can configure how big is your map, how many hospitals should go here. We have a function for adding a new house to the state space, and then some functions that are going to get me all of the available spaces for if I want to like randomly place hospitals in particular locations. And here now is the hill climbing algorithm. So what are we going to do in the hill climbing algorithm? Well, we're going to start by randomly initializing where the hospitals are going to go. We don't know where the hospitals should actually be, so let's just randomly place them. So here I'm running a loop for each of the hospitals that I have. I'm going to go ahead and add a new hospital at some random location. So I basically get all of the available spaces, and I randomly choose one of them as where I would like to add this particular hospital. I have some logging output and generating some images, which we'll take a look at a little bit later. But here is the key idea. So I'm going to just keep repeating this algorithm. I could specify a maximum of how many times I want it to run, or I could just run it up until it hits a local maximum or local minimum. And now we'll basically consider all of the hospitals that could potentially move. So consider each of the 2 hospitals or more hospitals if there are more than that. And consider all of the places where that hospital could move to, some neighbor of that hospital that we can move the neighbor to. And then see, is this going to be better than where we were currently? So if it is going to be better, then we'll go ahead and update our best neighbor and keep track of this new best neighbor that we found. And then afterwards, we can ask ourselves the question, if best neighbor cost is greater than or equal to the cost of the current set of hospitals, meaning if the cost of our best neighbor is greater than the current cost, meaning our best neighbor is worse than our current state, well, then we shouldn't make any changes at all, and we should just go ahead and return the current set of hospitals. But otherwise, we can update our hospitals in order to change them to one of the best neighbors. And if there are multiple that are all equivalent, I'm here using random.choice to say go ahead and choose one randomly. So this is really just a Python implementation of that same idea that we were just talking about, this idea of taking a current state, some current set of hospitals, generating all of the neighbors, looking at all of the ways we could take one hospital and move it one square to the left or right or up or down, and then figuring out, based on all of that information, which is the best neighbor or the set of all the best neighbors, and then choosing from one of those. And each time we go ahead and generate an image in order to do that. And so now what we're doing is if we look down at the bottom, I'm going to randomly generate a space with height 10 and width 20, and I'll say go ahead and put 3 hospitals somewhere in the space. I'll randomly generate 15 houses that I just go ahead and add in random locations. And now I'm going to run this hill climbing algorithm in order to try and figure out where we should place those hospitals. So I'll go ahead and run this program by running Python hospitals. And we see that we started, our initial state had a cost of 72, but we were able to continually find neighbors that were able to decrease that cost, decrease to 69, 66, 63, so on and so forth, all the way down to 53 as the best neighbor we were able to ultimately find. And we can take a look at what that looked like by just opening up these files. So here, for example, was the initial configuration. We randomly selected a location for each of these 15 different houses, and then randomly selected locations for 1, 2, 3 hospitals that were just located somewhere inside of this state space. And if you add up all the distances from each of the houses to their nearest hospital, you get a total cost of about 72. And so now the question is, what neighbors can we move to that improve this situation? And it looks like the first one the algorithm found was by taking this house that was over there on the right and just moving it to the left. And that probably makes sense because if you look at the houses in that general area, really these 5 houses look like they're probably the ones that are going to be closest to this hospital over here. Moving it to the left decreases the total distance, at least to most of these houses, though it does increase that distance for one of them. And so we're able to make these improvements to the situation by continually finding ways that we can move these hospitals around until we eventually settle at this particular state that has a cost of 53, where we figured out a position for each of the hospitals, and now none of the neighbors that we could move to are actually going to improve the situation. We can take this hospital and that hospital and look at each of the neighbors, and none of those are going to be better than this particular configuration. And again, that's not to say that this is the best we could do. There might be some other configuration of hospitals that is a global minimum, and this might just be a local minimum that is the best of all of its neighbors, but maybe not the best in the entire possible state space. And you could search through the entire state space by considering all of the possible configurations for hospitals. But ultimately, that's going to be very time intensive, especially as our state space gets bigger and there might be more and more possible states. It's going to take quite a long time to look through all of them. And so being able to use these sort of local search algorithms can often be quite good for trying to find the best solution we can do. And especially if we don't care about doing the best possible and we just care about doing pretty good and finding a pretty good placement of those hospitals, then these methods can be particularly powerful. But of course, we can try and mitigate some of this concern by, instead of using hill climbing, to use random restart. This idea of rather than just hill climb one time, we can hill climb multiple times and say, try hill climbing a whole bunch of times on the exact same map and figure out what is the best one that we've been able to find. And so I've here implemented a function for random restart that restarts some maximum number of times. And what we're going to do is repeat that number of times this process of just go ahead and run the hill climbing algorithm, figure out what the cost is of getting from all the houses to the hospitals, and then figure out, is this better than we've done so far? So I can try this exact same idea, where instead of running hill climbing, I'll go ahead and run random restart, and I'll randomly restart maybe 20 times, for example. And we'll go ahead and now I'll remove all the images and then rerun the program. And now we started by finding an original state when we initially ran hill climbing, the best cost we were able to find was 56. Each of these iterations is a different iteration of the hill climbing algorithm. We're running hill climbing not one time, but 20 times here, each time going until we find a local minimum, in this case. And we look and see each time, did we do better than we did the best time we've done so far? So we went from 56 to 46. This one was greater, so we ignored it. This one was 41, which was less, so we went ahead and kept that one. And for all of the remaining 16 times that we tried to implement hill climbing, and we tried to run the hill climbing algorithm, we couldn't do any better than that 41. Again, maybe there is a way to do better that we just didn't find, but it looks like that way ended up being a pretty good solution to the problem. That was attempt number 3, starting from counting at 0. So we can take a look at that, open up number 3, and this was the state that happened to have a cost of 41. That after running the hill climbing algorithm on some particular random initial configuration of hospitals, this is what we found was the local minimum in terms of trying to minimize the cost. And it looks like we did pretty well, that this hospital is pretty close to this region. This one is pretty close to these houses here. This hospital looks about as good as we can do for trying to capture those houses over on that side. And so these sorts of algorithms can be quite useful for trying to solve these problems. But the real problem with many of these different types of hill climbing, steepest ascent, stochastic, first choice, and so forth, is that they never make a move that makes our situation worse. Right? They're always going to take ourselves in our current state, look at the neighbors, and consider, can we do better than our current state, and move to one of those neighbors. Which of those neighbors we choose might vary among these various different types of algorithms, but we never go from a current position to a position that is worse than our current position. And ultimately, that's what we're going to need to do if we want to be able to find a global maximum or a global minimum. Because sometimes if we get stuck, we want to find some way of dislodging ourselves from our local maximum or local minimum in order to find the global maximum or the global minimum, or increase the probability that we do find it. And so the most popular technique for trying to approach the problem from that angle is a technique known as simulated annealing. Simulated because it's modeling after a real physical process of annealing, where you can think about this in terms of physics, a physical situation where you have some system of particles. And you might imagine that when you heat up a particular physical system, there's a lot of energy there. Things are moving around quite randomly. But over time, as the system cools down, it eventually settles into some final position. And that's going to be the general idea of simulated annealing. We're going to simulate that process of some high temperature system where things are moving around randomly quite frequently, but over time decreasing that temperature until we eventually settle at our ultimate solution. And the idea is going to be, if we have some state space landscape that looks like this, and we begin at an initial state here, if we're looking for a global maximum and we're trying to maximize the value of the state, our traditional hill climbing algorithms would just take the state and look at the two neighbor ones and always pick the one that is going to increase the value of the state. But if we want some chance of being able to find the global maximum, we can't always make good moves. We have to sometimes make bad moves and allow ourselves to make a move in a direction that actually seems, for now, to make our situation worse, such that later we can find our way up to that global maximum in terms of trying to solve that problem. Of course, once we get up to this global maximum, once we've done a whole lot of the searching, then we probably don't want to be moving to states that are worse than our current state. And so this is where this metaphor for annealing starts to come in, where we want to start making more random moves, and over time start to make fewer of those random moves based on a particular temperature schedule. So the basic outline looks something like this. Early on in simulated annealing, we have a higher temperature state. And what we mean by a higher temperature state is that we are more likely to accept neighbors that are worse than our current state. That we might look at our neighbors, and if one of our neighbors is worse than the current state, especially if it's not all that much worse, if it's pretty close but just slightly worse, then we might be more likely to accept that and go ahead and move to that neighbor anyways. But later on, as we run simulated annealing, we're going to decrease that temperature. And at a lower temperature, we're going to be less likely to accept neighbors that are worse than our current state. Now, to formalize this and put a little bit of pseudocode to it, here is what that algorithm might look like. We have a function called simulated annealing that takes as input the problem we're trying to solve, and also potentially some maximum number of times that we might want to run the simulated annealing process. How many different neighbors are we going to try and look for? And that value is going to vary based on the problem you're trying to solve. We'll again start with some current state that will be equal to the initial state of the problem. But now we need to repeat this process over and over for max number of times. Repeat some process some number of times, where we're first going to calculate a temperature. And this temperature function takes the current time t, starting at 1, going all the way up to max, and then gives us some temperature that we can use in our computation, where the idea is that this temperature is going to be higher early on, and it's going to be lower later on. So there are a number of ways this temperature function could often work. One of the simplest ways is just to say it is like the proportion of time that we still have remaining. Out of like max units of time, how much time do we have remaining? You start off with a lot of that time remaining, and as time goes on, the temperature is going to decrease because you have less and less of that remaining time still available to you. So we calculate a temperature for the current time. And then we pick a random neighbor of the current state. No longer are we going to be picking the best neighbor that we possibly can, or just one of the better neighbors that we can. We're going to pick a random neighbor. It might be better, it might be worse, but we're going to calculate that. We're going to calculate delta E, E for energy in this case, which is just how much better is the neighbor than the current state. So if delta E is positive, that means the neighbor is better than our current state. If delta E is negative, that means the neighbor is worse than our current state. And so we can then have a condition that looks like this. If delta E is greater than 0, that means the neighbor state is better than our current state. And if ever that situation arises, we'll just go ahead and update current to be that neighbor. Same as before, move where we are currently to be the neighbor, because the neighbor is better than our current state. We'll go ahead and accept that. But now the difference is that whereas before we never ever wanted to take a move that made our situation worse, now we sometimes want to make a move that is actually going to make our situation worse, because sometimes we're going to need to dislodge ourselves from a local minimum or local maximum to increase the probability that we're able to find the global minimum or the global maximum a little bit later. And so how do we do that? How do we decide to sometimes accept some state that might actually be worse? Well, we're going to accept a worse state with some probability. And that probability needs to be based on a couple of factors. It needs to be based in part on the temperature, where if the temperature is higher, we're more likely to move to a worse neighbor. And if the temperature is lower, we're less likely to move to a worse neighbor. But it also, to some degree, should be based on delta E. If the neighbor is much worse than the current state, we probably want to be less likely to choose that than if the neighbor is just a little bit worse than the current state. So again, there are a couple of ways you could calculate this, but it turns out one of the most popular is just to calculate e to the power of delta E over t, where e is just a constant. Delta E over t are based on delta E and t here. We calculate that value, and that'll be some value between 0 and 1. And that is the probability with which we should just say, all right, let's go ahead and move to that neighbor. And it turns out that if you do the math for this value, when delta E is such that the neighbor is not that much worse than the current state, that's going to be more likely that we're going to go ahead and move to that state. And likewise, when the temperature is lower, we're going to be less likely to move to that neighboring state as well. So now this is the big picture for simulated annealing. This process of taking the problem and going ahead and generating random neighbors. We'll always move to a neighbor if it's better than our current state. But even if the neighbor is worse than our current state, we'll sometimes move there, depending on how much worse it is, and also based on the temperature. And as a result, the hope, the goal of this whole process is that as we begin to try and find our way to the global maximum or the global minimum, we can dislodge ourselves if we ever get stuck at a local maximum or local minimum in order to eventually make our way to exploring the part of the state space that is going to be the best. And then as the temperature decreases, eventually we settle there without moving around too much from what we've found to be the globally best thing that we can do thus far. So at the very end, we just return whatever the current state happens to be, and that is the conclusion of this algorithm. We've been able to figure out what the solution is. And these types of algorithms have a lot of different applications. Anytime you can take a problem and formulate it as something where you can explore a particular configuration and then ask, are any of the neighbors better than this current configuration, and have some way of measuring that, then there's an applicable case for these hill climbing, simulated annealing types of algorithms. So sometimes it can be for facility location type problems, like for when you're trying to plan a city and figure out where the hospitals should be. But there are definitely other applications as well. And one of the most famous problems in computer science is the traveling salesman problem. Traveling salesman problem generally is formulated like this. I have a whole bunch of cities here indicated by these dots. And what I'd like to do is find some route that takes me through all of the cities and ends up back where I started. So some route that starts here, goes through all these cities, and ends up back where I originally started. And what I might like to do is minimize the total distance that I have to travel in order to, or the total cost of taking this entire path. And you can imagine this is a problem that's very applicable in situations like when delivery companies are trying to deliver things to a whole bunch of different houses. They want to figure out, how do I get from the warehouse to all these various different houses and get back again, all using as minimal time and distance and energy as possible. So you might want to try to solve these sorts of problems. But it turns out that solving this particular kind of problem is very computationally difficult. It is a very computationally expensive task to be able to figure it out. This falls under the category of what are known as NP-complete problems, problems that there is no known efficient way to try and solve these sorts of problems. And so what we ultimately have to do is come up with some approximations, some ways of trying to find a good solution, even if we're not going to find the globally best solution that we possibly can, at least not in a feasible or tractable amount of time. And so what we could do is take the traveling salesman problem and try to formulate it using local search and ask a question like, all right, I can pick some state, some configuration, some route between all of these nodes, and I can measure the cost of that state, figure out what the distance is. And I might now want to try to minimize that cost as much as possible. And then the only question now is, what does it mean to have a neighbor of this state? What does it mean to take this particular route and have some neighboring route that is close to it but slightly different, such that it might have a different total distance? And there are a number of different definitions for what a neighbor of a traveling salesman configuration might look like. But one way is just to say, a neighbor is what happens if we pick two of these edges between nodes and switch them effectively. So for example, I might pick these two edges here, these two that just happen to cross. This node goes here, this node goes there, and go ahead and switch them. And what that process will generally look like is removing both of these edges from the graph, taking this node, and connecting it to the node it wasn't connected to, so connecting it up here instead. We'll need to take these arrows that were originally going this way and reverse them, so move them going the other way, and then just fill in that last remaining blank. Add an arrow that goes in that direction instead. So by taking two edges and just switching them, I have been able to consider one possible neighbor of this particular configuration. And it looks like this neighbor is actually better. It looks like this probably travels a shorter distance in order to get through all the cities through this route than the current state did. And so you could imagine implementing this idea inside of a hill climbing or simulated annealing algorithm, where we repeat this process to try and take a state of this traveling salesman problem, look at all of the neighbors, and then move to the neighbors if they're better, or maybe even move to the neighbors if they're worse, until we eventually settle upon some best solution that we've been able to find. And it turns out that these types of approximation algorithms, even if they don't always find the very best solution, can often do pretty well at trying to find solutions that are helpful too. So that then was a look at local search, a particular category of algorithms that can be used for solving a particular type of problem, where we don't really care about the path to the solution. I didn't care about the steps I took to decide where the hospitals should go. I just cared about the solution itself. I just care about where the hospitals should be, or what the route through the traveling salesman journey really ought to be. Another type of algorithm that might come up are known as these categories of linear programming types of problems. And linear programming often comes up in the context where we're trying to optimize for some mathematical function. But oftentimes linear programming will come up when we might have real numbered values. That it's not just like discrete fixed values that we might have, but any decimal values that we might want to be able to calculate. And so linear programming is a family of types of problems where we might have a situation that looks like this, where the goal of linear programming is to minimize a cost function. And you can invert the numbers and say try and maximize it, but often we'll frame it as trying to minimize a cost function that has some number of variables, x1, x2, x3, all the way up to xn, just some number of variables that are involved, things that I want to know the values to. And this cost function might have coefficients in front of those variables. And this is what we would call like a linear equation, where we just have all of these variables that might be multiplied by a coefficient and then added together. We're not going to square anything or cube anything, because that'll give us different types of equations. With linear programming, we're just dealing with linear equations in addition to linear constraints, where a constraint is going to look something like, if we sum up this particular equation, that is just some linear combination of all of these variables, it is less than or equal to some bound b. And we might have a whole number of these various different constraints that we might place onto our linear programming exercise. And likewise, just as we can have constraints that are saying this linear equation is less than or equal to some bound b, it might also be equal to something. That if you want some sum of some combination of variables to be equal to a value, you can specify that. And we can also maybe specify that each variable has lower and upper bounds, that it needs to be a positive number, for example, or it needs to be a number that is less than 50, for example. And there are a number of other choices that we can make there for defining what the bounds of a variable are. But it turns out that if you can take a problem and formulate it in these terms, formulate the problem as your goal is to minimize a cost function, and you're minimizing that cost function subject to particular constraints, subject to equations that are of the form like this, of some sequence of variables is less than a bound or is equal to some particular value, then there are a number of algorithms that already exist for solving these sorts of problems. So let's go ahead and take a look at an example. Here's an example of a problem that might come up in the world of linear programming. Often this is going to come up when we're trying to optimize for something, and we want to be able to do some calculations, and we have constraints on what we're trying to optimize. And so it might be something like this. In the context of a factory, we have two machines, x1 and x2. x1 costs $50 an hour to run. x2 costs $80 an hour to run. And our goal, what we're trying to do, our objective, is to minimize the total cost. So that's what we'd like to do. But we need to do so subject to certain constraints. So there might be a labor constraint, that x1 requires 5 units of labor per hour, x2 requires 2 units of labor per hour, and we have a total of 20 units of labor that we have to spend. So this is a constraint. We have no more than 20 units of labor that we can spend, and we can spend it across x1 and x2, each of which requires a different amount of labor. And we might also have a constraint like this that tells us x1 is going to produce 10 units of output per hour, x2 is going to produce 12 units of output per hour, and the company needs 90 units of output. So we have some goal, something we need to achieve. We need to achieve 90 units of output, but there are some constraints that x1 can only produce 10 units of output per hour, x2 produces 12 units of output per hour. These types of problems come up quite frequently, and you can start to notice patterns in these types of problems. Problems where I am trying to optimize for some goal, minimizing cost, maximizing output, maximizing profits, or something like that, and there are constraints that are placed on that process. And so now we just need to formulate this problem in terms of linear equations. So let's start with this first point. Two machines, x1 and x2. X costs $50 an hour, x2 costs $80 an hour. Here we can come up with an objective function that might look like this. This is our cost function, rather. 50 times x1 plus 80 times x2, where x1 is going to be a variable representing how many hours do we run machine x1 for. x2 is going to be a variable representing how many hours are we running machine x2 for. And what we're trying to minimize is this cost function, which is just how much it costs to run each of these machines per hour summed up. This is an example of a linear equation, just some combination of these variables plus coefficients that are placed in front of them. And I would like to minimize that total value. But I need to do so subject to these constraints. x1 requires 50 units of labor per hour, x2 requires 2, and we have a total of 20 units of labor to spend. And so that gives us a constraint of this form. 5 times x1 plus 2 times x2 is less than or equal to 20. 20 is the total number of units of labor we have to spend, and that's spent across x1 and x2, each of which requires a different number of units of labor per hour, for example. And finally, we have this constraint here. x1 produces 10 units of output per hour, x2 produces 12, and we need 90 units of output. And so this might look something like this. That 10x1 plus 12x2, this is amount of output per hour, it needs to be at least 90. If we can do better, great, but it needs to be at least 90. And if you recall from my formulation before, I said that generally speaking in linear programming, we deal with equals constraints or less than or equal to constraints. So we have a greater than or equal to sign here. That's not a problem. Whenever we have a greater than or equal to sign, we can just multiply the equation by -1, and that'll flip it around to a less than or equals -90, for example, instead of a greater than or equal to 90. And that's going to be an equivalent expression that we can use to represent this problem. So now that we have this cost function and these constraints that it's subject to, it turns out there are a number of algorithms that can be used in order to solve these types of problems. And these problems go a little bit more into geometry and linear algebra than we're really going to get into. But the most popular of these types of algorithms are simplex, which was one of the first algorithms discovered for trying to solve linear programs. And later on, a class of interior point algorithms can be used to solve this type of problem as well. The key is not to understand exactly how these algorithms work, but to realize that these algorithms exist for efficiently finding solutions anytime we have a problem of this particular form. And so we can take a look, for example, at the production directory here, where here I have a file called production.py, where here I'm using SciPy, which is a library for a lot of science-related functions within Python. And I can go ahead and just run this optimization function in order to run a linear program. .linprog here is going to try and solve this linear program for me, where I provide to this expression, to this function call, all of the data about my linear program. So it needs to be in a particular format, which might be a little confusing at first. But this first argument to scipy.optimize.linprogramming is the cost function, which is in this case just an array or a list that has 50 and 80, because my original cost function was 50 times x1 plus 80 times x2. So I just tell Python 50 and 80, those are the coefficients that I am now trying to optimize for. And then I provide all of the constraints. So the constraints, and I wrote them up above in comments, is the constraint 1 is 5x1 plus 2x2 is less than or equal to 20. And constraint 2 is negative 10x1 plus negative 12x2 is less than or equal to negative 90. And so SciPy expects these constraints to be in a particular format. It first expects me to provide all of the coefficients for the upper bound equations, UB is just short for upper bound, where the coefficients of the first equation are 5 and 2, because we have 5x1 and 2x2. And the coefficients for the second equation are negative 10 and negative 12, because I have negative 10x1 plus negative 12x2. And then here, we provide it as a separate argument, just to keep things separate, what the actual bound is. What is the upper bound for each of these constraints? Well, for the first constraint, the upper bound is 20. That was constraint number 1. And then for constraint number 2, the upper bound is 90. So a bit of a cryptic way of representing it. It's not quite as simple as just writing the mathematical equations. What really is being expected here are all of the coefficients and all of the numbers that are in these equations, by first providing the coefficients for the cost function, then providing all the coefficients for the inequality constraints, and then providing all of the upper bounds for those inequality constraints. And once all of that information is there, then we can run any of these interior point algorithms or the simplex algorithm. Even if you don't understand how it works, you can just run the function and figure out what the result should be. And here I said, if the result is a success, we were able to solve this problem, go ahead and print out what the value of x1 and x2 should be. Otherwise, go ahead and print out no solution. And so if I run this program by running python production.py, it takes a second to calculate, but then we see here is what the optimal solution should be. x1 should run for 1.5 hours. x2 should run for 6.25 hours. And we were able to do this by just formulating the problem as a linear equation that we were trying to optimize, some cost that we were trying to minimize, and then some constraints that were placed on that. And many, many problems fall into this category of problems that you can solve if you can just figure out how to use equations and use these constraints to represent that general idea. And that's a theme that's going to come up a couple of times today, where we want to be able to take some problem and reduce it down to some problem we know how to solve in order to begin to find a solution, and to use existing methods that we can use in order to find a solution more effectively or more efficiently. And it turns out that these types of problems, where we have constraints, show up in other ways too. And there's an entire class of problems that's more generally just known as constraint satisfaction problems. And we're going to now take a look at how you might formulate a constraint satisfaction problem and how you might go about solving a constraint satisfaction problem. But the basic idea of a constraint satisfaction problem is we have some number of variables that need to take on some values, and we need to figure out what values each of those variables should take on. But those variables are subject to particular constraints that are going to limit what values those variables can actually take on. So let's take a look at a real-world example, for example. Let's look at exam scheduling. that I have 4 students here, students 1, 2, 3, and 4. Each of them is taking some number of different classes. Classes here are going to be represented by letters. So student 1 is enrolled in courses A, B, and C. Student 2 is enrolled in courses B, D, and E, so on and so forth. And now, say a university, for example, is trying to schedule exams for all of these courses. But there are only 3 exam slots on Monday, Tuesday, and Wednesday. And we have to schedule an exam for each of these courses. But the constraint now, the constraint we have to deal with the scheduling, is that we don't want anyone to have to take 2 exams on the same day. We would like to try and minimize that or eliminate it if at all possible. So how do we begin to represent this idea? How do we structure this in a way that a computer with an AI algorithm can begin to try and solve the problem? Well, let's in particular just look at these classes that we might take and represent each of the courses as some node inside of a graph. And what we'll do is we'll create an edge between 2 nodes in this graph if there is a constraint between those 2 nodes. So what does this mean? Well, we can start with student 1, who's enrolled in courses A, B, and C. What that means is that A and B can't have an exam at the same time. A and C can't have an exam at the same time. And B and C also can't have an exam at the same time. And I can represent that in this graph by just drawing edges. One edge between A and B, one between B and C, and then one between C and A. And that encodes now the idea that between those nodes there is a constraint. And in particular, the constraint happens to be that these 2 can't be equal to each other, though there are other types of constraints that are possible, depending on the type of problem that you're trying to solve. And then we can do the same thing for each of the other students. So for student 2, who's enrolled in courses B, D, and E, well, that means B, D, and E, those all need to have edges that connect each other as well. Student 3 is enrolled in courses C, E, and F. So we'll go ahead and take C, E, and F and connect those by drawing edges between them too. And then finally, student 4 is enrolled in courses E, F, and G. And we can represent that by drawing edges between E, F, and G, although E and F already had an edge between them. We don't need another one, because this constraint is just encoding the idea that course E and course F cannot have an exam on the same day. So this, then, is what we might call the constraint graph. It is some graphical representation of all of my variables, so to speak, and the constraints between those possible variables, where in this particular case, each of the constraints represents an inequality constraint, that an edge between B and D means whatever value the variable B takes on cannot be the value that the variable D takes on as well. So what then actually is a constraint satisfaction problem? Well, a constraint satisfaction problem is just some set of variables, x1 all the way through xn, some set of domains for each of those variables. So every variable needs to take on some values. Maybe every variable has the same domain, but maybe each variable has a slightly different domain. And then there's a set of constraints, and we'll just call a set C, that is some constraints that are placed upon these variables. Like x1 is not equal to x2. But they could be of other forms too, like maybe x1 equals x2 plus 1, if these variables are taking on numerical values in their domain, for example. The types of constraints are going to vary based on the types of problems. And constraint satisfaction shows up all over the place as well, in any situation where we have variables that are subject to particular constraints. So one popular game is Sudoku, for example, this 9x9 grid where you need to fill in numbers into each of these cells, but you don't want to make sure there's never a duplicate number in any row or in any column or in any grid of 3x3 cells, for example. So what might this look like as a constraint satisfaction problem? Well, my variables are all of the empty squares in the puzzle. So represented here is just like an x, y coordinate, for example, as all of the squares where I need to plug in a value, where I don't know what value it should take on. The domain is just going to be all of the numbers from 1 through 9, any value that I could fill in to one of these cells. So that is going to be the domain for each of these variables. And then the constraints are going to be of the form like this cell can't be equal to this cell, can't be equal to this cell, can't be. All of these need to be different, for example. And same for all of the rows and the columns and the 3x3 squares as well. So those constraints are going to enforce what values are actually allowed. And we can formulate the same idea in the case of this exam scheduling problem, where the variables we have are the different courses, A up through G. The domain for each of these variables is going to be Monday, Tuesday, and Wednesday. Those are the possible values each of the variables can take on, that in this case just represent when is the exam for that class. And then the constraints are of this form. A is not equal to B, A is not equal to C, meaning A and B can't have an exam on the same day, A and C can't have an exam on the same day, or more formally, these two variables cannot take on the same value within their domain. So that then is this formulation of a constraint satisfaction problem that we can begin to use to try and solve this problem. And constraints can come in a number of different forms. There are hard constraints, which are constraints that must be satisfied for a correct solution. So something like in the Sudoku puzzle, you cannot have this cell and this cell that are in the same row take on the same value. That is a hard constraint. But problems can also have soft constraints, where these are constraints that express some notion of preference, that maybe A and B can't have an exam on the same day, but maybe someone has a preference that A's exam is earlier than B's exam. It doesn't need to be the case, but there's some expression that some solution is better than another solution. And in that case, you might formulate the problem as trying to optimize for maximizing people's preferences. You want people's preferences to be satisfied as much as possible. In this case, though, we'll mostly just deal with hard constraints, constraints that must be met in order to have a correct solution to the problem. So we want to figure out some assignment of these variables to their particular values that is ultimately going to give us a solution to the problem by allowing us to assign some day to each of the classes such that we don't have any conflicts between classes. So it turns out that we can classify the constraints in a constraint satisfaction problem into a number of different categories. The first of those categories are perhaps the simplest of the types of constraints, which are known as unary constraints, where a unary constraint is a constraint that just involves a single variable. For example, a unary constraint might be something like A does not equal Monday, meaning course A cannot have its exam on Monday. If for some reason the instructor for the course isn't available on Monday, you might have a constraint in your problem that looks like this, something that just has a single variable A in it, and maybe says A is not equal to Monday, or A is equal to something, or in the case of numbers, greater than or less than something, a constraint that just has one variable we consider to be a unary constraint. And this is in contrast to something like a binary constraint, which is a constraint that involves two variables, for example. So this would be a constraint like the ones we were looking at before. Something like A does not equal B is an example of a binary constraint, because it is a constraint that has two variables involved in it, A and B, and we represented that using some arc or some edge that connects variable A to variable B. And using this knowledge of, OK, what is a unary constraint, what is a binary constraint, there are different types of things we can say about a particular constraint satisfaction problem. And one thing we can say is we can try and make the problem node consistent. So what does node consistency mean? Node consistency means we have all of the values in a variable's domain satisfying that variable's unary constraints. So for each of the variables inside of our constraint satisfaction problem, if all of the values satisfy the unary constraints for that particular variable, we can say that the entire problem is node consistent, or we can even say that a particular variable is node consistent if we just want to make one node consistent within itself. So what does that actually look like? Let's look at now a simplified example where instead of having a whole bunch of different classes, we just have two classes, A and B, each of which has an exam on either Monday or Tuesday or Wednesday. So this is the domain for the variable A, and this is the domain for the variable B. And now let's imagine we have these constraints. A not equal to Monday, B not equal to Tuesday, B not equal to Monday, A not equal to B. So those are the constraints that we have on this particular problem. And what we can now try to do is enforce node consistency. And node consistency just means we make sure that all of the values for any variable's domain satisfy its unary constraints. And so we could start by trying to make node A node consistent. Like, is it consistent? Does every value inside of A's domain satisfy its unary constraints? Well, initially we'll see that Monday does not satisfy A's unary constraints, because we have a constraint, a unary constraint here, that A is not equal to Monday, but Monday is still in A's domain. And so this is something that is not node consistent, because we have Monday in the domain, but this is not a valid value for this particular node. And so how do we make this node consistent? Well, to make the node consistent, what we'll do is we'll just go ahead and remove Monday from A's domain. Now A can only be on Tuesday or Wednesday, because we had this constraint that said A is not equal to Monday. And at this point now, A is node consistent. For each of the values that A can take on, Tuesday and Wednesday, there is no constraint that is a unary constraint that conflicts with that idea. There is no constraint that says that A can't be Tuesday. There's no unary constraint that says that A cannot be on Wednesday. And so now we can turn our attention to B. B also has a domain, Monday, Tuesday, and Wednesday. And we can begin to see whether those variables satisfy the unary constraints as well. Well, here's a unary constraint. B is not equal to Tuesday. And that does not appear to be satisfied by this domain of Monday, Tuesday, and Wednesday, because Tuesday, this possible value that the variable B could take on, is not consistent with this unary constraint, that B is not equal to Tuesday. So to solve that problem, we'll go ahead and remove Tuesday from B's domain. Now B's domain only contains Monday and Wednesday, but as it turns out, there's yet another unary constraint that we placed on the variable B, which is here. B is not equal to Monday. That means that this value, Monday, inside of B's domain, is not consistent with B's unary constraints, because we have a constraint that says that B cannot be Monday, and so we can remove Monday from B's domain. And now we've made it through all of the unary constraints. We've not yet considered this constraint, which is a binary constraint. But we've considered all of the unary constraints, all of the constraints that involve just a single variable. And we've made sure that every node is consistent with those unary constraints. So we can say that now we have enforced node consistency, that for each of these possible nodes, we can pick any of these values in the domain, and there won't be a unary constraint that is violated as a result of it. So node consistency is fairly easy to enforce. We just take each node, make sure the values in the domain satisfy the unary constraints. Where things get a little bit more interesting is when we consider different types of consistency, something like arc consistency, for example. And arc consistency refers to when all of the values in a variable's domain satisfy the variable's binary constraints. So when we're looking at trying to make A arc consistent, we're no longer just considering the unary constraints that involve A. We're trying to consider all of the binary constraints that involve A as well. So any edge that connects A to another variable inside of that constraint graph that we were taking a look at before. Put a little bit more formally, arc consistency, and arc really is just another word for like an edge that connects two of these nodes inside of our constraint graph. We can define arc consistency a little more precisely like this. In order to make some variable x arc consistent with respect to some other variable y, we need to remove any element from x's domain to make sure that every choice for x, every choice in x's domain, has a possible choice for y. So put another way, if I have a variable x and I want to make x arc consistent, then I'm going to look at all of the possible values that x can take on and make sure that for all of those possible values, there is still some choice that I can make for y, if there's some arc between x and y, to make sure that y has a possible option that I can choose as well. So let's look at an example of that. Going back to this example from before, we enforced node consistency already by saying that A can only be on Tuesday or Wednesday, because we knew that A could not be on Monday. And we also said that B's only domain only consists of Wednesday, because we know that B does not equal Tuesday, and also B does not equal Monday. So now let's begin to consider arc consistency. Let's try and make A arc consistent with B. And what that means is to make A arc consistent with respect to B means that for any choice we make in A's domain, there is some choice we can make in B's domain that is going to be consistent. And we can try that. For A, we can choose Tuesday as a possible value for A. If I choose Tuesday for A, is there a value for B that satisfies the binary constraint? Well, yes, B Wednesday would satisfy this constraint that A does not equal B, because Tuesday does not equal Wednesday. However, if we chose Wednesday for A, well then there is no choice in B's domain that satisfies this binary constraint. There is no way I can choose something for B that satisfies A does not equal B, because I know B must be Wednesday. And so if ever I run into a situation like this, where I see that here is a possible value for A, such that there is no choice of value for B that satisfies the binary constraint, well then this is not arc consistent. And to make it arc consistent, I would need to take Wednesday and remove it from A's domain, because Wednesday was not going to be a possible choice I could make for A, because it wasn't consistent with this binary constraint for B. There was no way I could choose Wednesday for A and still have an available solution by choosing something for B as well. So here now I've been able to enforce arc consistency. And in doing so, I've actually solved this entire problem, that given these constraints where A and B can have exams on either Monday or Tuesday or Wednesday, the only solution, as it would appear, is that A's exam must be on Tuesday and B's exam must be on Wednesday. And that is the only option available to me. So if we want to apply our consistency to a larger graph, not just looking at one particular pair of our consistency, there are ways we can do that too. And we can begin to formalize what the pseudocode would look like for trying to write an algorithm that enforces arc consistency. And we'll start by defining a function called revise. Revise is going to take as input a CSP, otherwise known as a constraint satisfaction problem, and also two variables x and y. And what revise is going to do is it is going to make x arc consistent with respect to y, meaning remove anything from x's domain that doesn't allow for a possible option for y. How does this work? Well, we'll go ahead and first keep track of whether or not we've made a revision. Revise is ultimately going to return true or false. It'll return true in the event that we did make a revision to x's domain. It'll return false if we didn't make any change to x's domain. And we'll see in a moment why that's going to be helpful. But we start by saying revised equals false. We haven't made any changes. Then we'll say, all right, let's go ahead and loop over all of the possible values in x's domain. So loop over x's domain for each little x in x's domain. I want to make sure that for each of those choices, I have some available choice in y that satisfies the binary constraints that are defined inside of my CSP, inside of my constraint satisfaction problem. So if ever it's the case that there is no value y in y's domain that satisfies the constraint for x and y, well, if that's the case, that means that this value x shouldn't be in x's domain. So I'll go ahead and delete x from x's domain, and I'll set revised equal to true, because I did change x's domain. I changed x's domain by removing little x, and I removed little x because it wasn't arc consistent. There was no way I could choose a value for y that would satisfy this xy constraint. So in this case, we'll go ahead and set revised equal true. And we'll do this again and again for every value in x's domain. Sometimes it might be fine. In other cases, it might not allow for a possible choice for y, in which case we need to remove this value from x's domain. And at the end, we just return revised to indicate whether or not we actually made a change. So this function then, this revise function, is effectively an implementation of what you saw me do graphically a moment ago. And it makes one variable, x, arc consistent with another variable, in this case y. But generally speaking, when we want to enforce arc consistency, we'll often want to enforce arc consistency not just for a single arc, but for the entire constraint satisfaction problem. And it turns out there's an algorithm to do that as well, and that algorithm is known as AC3. AC3 takes a constraint satisfaction problem, and it enforces arc consistency across the entire problem. How does it do that? Well, it's going to basically maintain a queue, or basically just a line of all of the arcs that it needs to make consistent. And over time, we might remove things from that queue as we begin dealing with arc consistency. And we might need to add things to that queue as well if there are more things we need to make arc consistent. So we'll go ahead and start with a queue that contains all of the arcs in the constraint satisfaction problem, all of the edges that connect two nodes that have some sort of binary constraint between them. And now, as long as the queue is non-empty, there is work to be done. The queue is all of the things that we need to make arc consistent. So as long as the queue is non-empty, there's still things we have to do. What do we have to do? Well, we'll start by dequeuing from the queue. Remove something from the queue. And strictly speaking, it doesn't need to be a queue, but a queue is a traditional way of doing this. We'll dequeue from the queue, and that'll give us an arc, x and y, these two variables where I would like to make x arc consistent with y. So how do we make x arc consistent with y? Well, we can go ahead and just use that revise function that we talked about a moment ago. We call the revise function, passing as input the constraint satisfaction problem, and also these variables x and y, because I want to make x arc consistent with y. In other words, remove any values from x's domain that don't leave an available option for y. And recall, what does revised return? Well, it returns true if we actually made a change, if we removed something from x's domain because there wasn't an available option for y, for example. And it returns false if we didn't make any change to x's domain at all. And it turns out if revise returns false, if we didn't make any changes, well, then there's not a whole lot more work to be done here for this arc. We can just move ahead to the next arc that's in the queue. But if we did make a change, if we did reduce x's domain by removing values from x's domain, well then what we might realize is that this creates potential problems later on. That it might mean that some arc that was arc consistent with x, that node might no longer be arc consistent with x, because while there used to be an option that we could choose for x, now there might not be, because now we might have removed something from x that was necessary for some other arc to be arc consistent. And so if ever we did revise x's domain, we're going to need to add some things to the queue, some additional arcs that we might want to check. How do we do that? Well, first thing we want to check is to make sure that x's domain is not 0. If x's domain is 0, that means there are no available options for x at all. And that means that there's no way you can solve the constraint satisfaction problem. If we've removed everything from x's domain, we'll go ahead and just return false here to indicate there's no way to solve the problem because there's nothing left in x's domain. But otherwise, if there are things left in x's domain, but fewer things than before, well, then what we'll do is we'll loop over each variable z that is in all of x's neighbors except for y. Y we already handled. But we'll consider all of x's others neighbors and ask ourselves, all right, well, that arc from each of those z's to x, that arc might no longer be arc consistent. Because while for each z, there might have been a possible option we could choose for x to correspond with each of z's possible values, now there might not be because we removed some elements from x's domain. And so what we'll do here is we'll go ahead and enqueue, adding something to the queue, this arc zx for all of those neighbors z. So we need to add back some arcs to the queue in order to continue to enforce arc consistency. At the very end, if we make it through all this process, then we can return true. But this now is AC3, this algorithm for enforcing arc consistency on a constraint satisfaction problem. And the big idea is really just keep track of all of the arcs that we might need to make arc consistent, make it arc consistent by calling the revise function. And if we did revise it, then there are some new arcs that might need to be added to the queue in order to make sure that everything is still arc consistent, even after we've removed some of the elements from a particular variable's domain. So what then would happen if we tried to enforce arc consistency on a graph like this, on a graph where each of these variables has a domain of Monday, Tuesday, and Wednesday? Well, it turns out that by enforcing arc consistency on this graph, while it can solve some types of problems, nothing actually changes here. For any particular arc, just considering two variables, there's always a way for me to just, for any of the choices I make for one of them, make a choice for the other one, because there are three options, and I just need the two to be different from each other. So this is actually quite easy to just take an arc and just declare that it is arc consistent, because if I pick, Monday for D, then I just pick something that isn't Monday for B. In arc consistency, we only consider consistency between a binary constraint between two nodes, and we're not really considering all of the rest of the nodes yet. So just using AC3, the enforcement of arc consistency, that can sometimes have the effect of reducing domains to make it easier to find solutions, but it will not always actually solve the problem. We might still need to somehow search to try and find a solution. And we can use classical traditional search algorithms to try to do so. You'll recall that a search problem generally consists of these parts. We have some initial state, some actions, a transition model that takes me from one state to another state, a goal test to tell me, have I satisfied my objective correctly, and then some path cost function, because in the case of like maze solving, I was trying to get to my goal as quickly as possible. So you could formulate a CSP, or a constraint satisfaction problem, as one of these types of search problems. The initial state will just be an empty assignment, where an assignment is just a way for me to assign any particular variable to any particular value. So if an empty assignment is no variables are assigned to any values yet, then the action I can take is adding some new variable equals value pair to that assignment, saying for this assignment, let me add a new value for this variable. And the transition model just defines what happens when you take that action. You get a new assignment that has that variable equal to that value inside of it. The goal test is just checking to make sure all the variables have been assigned and making sure all the constraints have been satisfied. And the path cost function, sort of irrelevant. I don't really care about what the path really is. I just care about finding some assignment that actually satisfies all of the constraints. So really, all the paths have the same cost. I don't really care about the path to the goal. I just care about the solution itself, much as we've talked about now before. The problem here, though, is that if we just implement this naive search algorithm just by implementing like breadth first search or depth first search, this is going to be very, very inefficient. And there are ways we can take advantage of efficiencies in the structure of a constraint satisfaction problem itself. And one of the key ideas is that we can really just order these variables, and it doesn't matter what order we assign variables in. The assignment a equals 2 and then b equals 8 is identical to the assignment of b equals 8 and then a equals 2. Switching the order doesn't really change anything about the fundamental nature of that assignment. And so there are some ways that we can try and revise this idea of a search algorithm to apply it specifically for a problem like a constraint satisfaction problem. And it turns out the search algorithm we'll generally use when talking about constraint satisfaction problems is something known as backtracking search. And the big idea of backtracking search is we'll go ahead and make assignments from variables to values. And if ever we get stuck, we arrive at a place where there is no way we can make any forward progress while still preserving the constraints that we need to enforce, we'll go ahead and backtrack and try something else instead. So the very basic sketch of what backtracking search looks like is it looks like this. Function called backtrack that takes as input an assignment and a constraint satisfaction problem. So initially, we don't have any assigned variables. So when we begin backtracking search, this assignment is just going to be the empty assignment with no variables inside of it. But we'll see later this is going to be a recursive function. So backtrack takes as input the assignment and the problem. If the assignment is complete, meaning all of the variables have been assigned, we just return that assignment. That, of course, won't be true initially, because we start with an empty assignment. But over time, we might add things to that assignment. So if ever the assignment actually is complete, then we're done. Then just go ahead and return that assignment. But otherwise, there's some work to be done. So what we'll need to do is select an unassigned variable for this particular problem. So we need to take the problem, look at the variables that have already been assigned, and pick a variable that has not yet been assigned. And I'll go ahead and take that variable. And then I need to consider all of the values in that variable's domain. So we'll go ahead and call this domain values function. We'll talk a little more about that later. That takes a variable and just gives me back an ordered list of all of the values in its domain. So I've taken a random unselected variable. I'm going to loop over all of the possible values. And the idea is let me just try all of these values as possible values for the variable. So if the value is consistent with the assignment so far, it doesn't violate any of the constraints, well then let's go ahead and add variable equals value to the assignment because it's so far consistent. And now let's recursively call backtrack to try and make the rest of the assignments also consistent. So I'll go ahead and call backtrack on this new assignment that I've added the variable equals value to. And now I recursively call backtrack and see what the result is. And if the result isn't a failure, well, then let me just return that result. And otherwise, what else could happen? Well, if it turns out the result was a failure, well, then that means this value was probably a bad choice for this particular variable, because when I assigned this variable equal to that value, eventually down the road, I ran into a situation where I violated constraints. There was nothing more I could do. So now I'll remove variable equals value from the assignment, effectively backtracking to say, all right, that value didn't work. Let's try another value instead. And then at the very end, if we were never able to return a complete assignment, we'll just go ahead and return failure, because that means that none of the values worked for this particular variable. This now is the idea for backtracking search, to take each of the variables, try values for them, and recursively try backtracking search, see if we can make progress. And if ever we run into a dead end, we run into a situation where there is no possible value we can choose that satisfies the constraints, we return failure, and that propagates up, and eventually we make a different choice by going back and trying something else instead. So let's put this algorithm into practice. Let's actually try and use backtracking search to solve this problem now, where I need to figure out how to assign each of these courses to an exam slot on Monday or Tuesday or Wednesday in such a way that it satisfies these constraints, that each of these edges mean those two classes cannot have an exam on the same day. So I can start by just starting at a node. It doesn't really matter which I start with, but in this case, I'll just start with A. And I'll ask a question like, all right, let me loop over the values in the domain. And maybe in this case, I'll just start with Monday and say, all right, let's go ahead and assign A to Monday. We'll just go in order Monday, Tuesday, Wednesday. And now let's consider node B. All right, so I've made an assignment to A, so I recursively call backtrack with this new part of the assignment. Now I'm looking to pick another unassigned variable like B. And I'll say, all right, maybe I'll start with Monday, because that's the very first value in B's domain. And I ask, all right, does Monday violate any constraints? And it turns out, yes, it does. It violates this constraint here between A and B, because A and B are now both on Monday. And that doesn't work, because B can't be on the same day as A. So that doesn't work. So we might instead try Tuesday. Try the next value in B's domain. And is that consistent with the assignment so far? Well, yeah. B Tuesday, A Monday, that is consistent so far, because they're not on the same day. So that's good. Now we can recursively call backtrack, try again. Pick another unassigned variable, something like D, and say, all right, let's go through its possible values. Is Monday consistent with this assignment? Well, yes, it is. B and D are on different days, Monday versus Tuesday. And A and B are also on different days, Monday versus Tuesday. So that's fine so far, too. We'll go ahead and try again. Maybe we'll go to this variable here, E. Say, can we make that consistent? Let's go through the possible values. We've recursively called backtrack. We might start with Monday and say, all right, that's not consistent, because D and E now have exams on the same day. So we might try Tuesday instead, going to the next one. Ask, is that consistent? Well, no, it's not, because B and E, those have exams on the same day. And so we try, all right, is Wednesday consistent? And it turns out, all right, yes, it is. Wednesday is consistent because D and E now have exams on different days. B and E now have exams on different days. All seems to be well so far. I recursively call backtrack, select another unassigned variable. We'll say maybe choose C this time. And say, all right, let's try the values that C could take on. Let's start with Monday. And it turns out that's not consistent, because now A and C both have exams on the same day. So I try Tuesday and say that's not consistent either, because B and C now have exams on the same day. And then I say, all right, let's go ahead and try Wednesday. But that's not consistent either, because C and E each have exams on the same day too. So now we've gone through all of the possible values for C, Monday, Tuesday, and Wednesday, and none of them are consistent. There is no way we can have a consistent assignment. Backtrack in this case will return failure. And so then we'd say, all right, we have to backtrack back to here. Well, now for E, we've tried all of Monday, Tuesday, and Wednesday, and none of those work, because Wednesday, which seemed to work, turned out to be a failure. So that means there's no possible way we can assign E. So that's a failure too. We have to go back up to D, which means that Monday assignment to D, that must be wrong. We must try something else. So we can try, all right, what if instead of Monday, we try Tuesday? Tuesday, it turns out, is not consistent, because B and D now have an exam on the same day. But Wednesday, as it turns out, works. And now we can begin to make some forward progress again. We go back to E and say, all right, which of these values works? Monday turns out to work by not violating any constraints. Then we go up to C now. Monday doesn't work because it violates a constraint. Violates two, actually. Tuesday doesn't work because it violates a constraint as well. But Wednesday does work. Then we can go to the next variable, F, and say, all right, does Monday work? Well, no, it violates a constraint. But Tuesday does work. And then finally, we can look at the last variable, G, recursively calling backtrack one more time. Monday is inconsistent. That violates a constraint. Tuesday also violates a constraint. But Wednesday, that doesn't violate a constraint. And so now at this point, we recursively call backtrack one last time. We now have a satisfactory assignment of all of the variables. And at this point, we can say that we are now done. We have now been able to successfully assign a variable or a value to each one of these variables in such a way that we're not violating any constraints. We're going to go ahead and have classes A and E have their exams on Monday. Classes B and F can have their exams on Tuesday. And classes C, D, and G can have their exams on Wednesday. And there's no violated constraints that might come up there. So that then was a graphical look at how this might work. Let's now take a look at some code we could use to actually try and solve this problem as well. So here I'll go ahead and go into the scheduling directory. We're here now. We'll start by looking at schedule0.py, where here I define a list of variables, A, B, C, D, E, F, G. Those are all of the different classes. Then underneath that, I define my list of constraints. So constraint A and B, that is a constraint because they can't be on the same day. Likewise, A and C, B and C, so on and so forth, enforcing those exact same constraints. And here then is what the backtracking function might look like. First, if the assignment is complete, if I've made an assignment of every variable to a value, go ahead and just return that assignment. Then we'll select an unassigned variable from that assignment. Then for each of the possible values in the domain, Monday, Tuesday, Wednesday, let's go ahead and create a new assignment that assigns the variable to that value. I'll call this consistent function, which I'll show you in a moment, that just checks to make sure this new assignment is consistent. But if it is consistent, we'll go ahead and call backtrack to go ahead and continue trying to run backtracking search. And as long as the result is not none, meaning it wasn't a failure, we can go ahead and return that result. But if we make it through all the values and nothing works, then it is a failure. There's no solution. We go ahead and return none here. What do these functions do? Select unassigned variable is just going to choose a variable not yet assigned. So it's going to loop over all the variables. And if it's not already assigned, we'll go ahead and just return that variable. And what does the consistent function do? Well, the consistent function goes through all the constraints. And if we have a situation where we've assigned both of those values to variables, but they are the same, well, then that is a violation of the constraint, in which case we'll return false. But if nothing is inconsistent, then the assignment is consistent and will return true. And then all the program does is it calls backtrack on an empty assignment, an empty dictionary that has no variable assigned and no values yet, save that inside a solution, and then print out that solution. So by running this now, I can run Python schedule0.py. And what I get as a result of that is an assignment of all these variables to values. And it turns out we assigned A to Monday as we would expect, B to Tuesday, C to Wednesday, exactly the same type of thing we were talking about before, an assignment of each of these variables to values that doesn't violate any constraints. And I had to do a fair amount of work in order to implement this idea myself. I had to write the backtrack function that went ahead and went through this process of recursively trying to do this backtracking search. But it turns out the constraint satisfaction problems are so popular that there exist many libraries that already implement this type of idea. Again, as with before, the specific library is not as important as the fact that libraries do exist. This is just one example of a Python constraint library where now, rather than having to do all the work from scratch inside of schedule1.py, I'm just taking advantage of a library that implements a lot of these ideas already. So here, I create a new problem, add variables to it with particular domains. I add a whole bunch of these individual constraints where I call add constraint and pass in a function describing what the constraint is. And the constraint basically says it's a function that takes two variables, x and y, and makes sure that x is not equal to y, enforcing the idea that these two classes cannot have exams on the same day. And then, for any constraint satisfaction problem, I can call getSolutions to get all the solutions to that problem. And then for each of those solutions, print out what that solution happens to be. And if I run Python schedule1.py, I now see there are actually a number of different solutions that can be used to solve the problem. There are, in fact, 6 different solutions, assignments of variables to values, that will give me a satisfactory answer to this constraint satisfaction problem. So this then was an implementation of a very basic backtracking search method, where really we just went through each of the variables, picked one that wasn't assigned, tried the possible values the variable could take on, and then if it worked, if it didn't violate any constraints, then we kept trying other variables. And if ever we hit a dead end, we had to backtrack. But ultimately, we might be able to be a little bit more intelligent about how we do this in order to improve the efficiency of how we solve these sorts of problems. And one thing we might imagine trying to do is going back to this idea of inference, using the knowledge we know to be able to draw conclusions in order to make the rest of the problem-solving process a little bit easier. And let's now go back to where we got stuck in this problem the first time. When we were solving this constraint satisfaction problem, we dealt with B. And then we went on to D, and we went ahead and just assigned D to Monday, because that seemed to work with the assignment so far. It didn't violate any constraints. But it turned out that later on, that choice turned out to be a bad one, that choice wasn't consistent with the rest of the values that we could take on here. And the question is there anything we could do to avoid getting into a situation like this, avoid trying to go down a path that's ultimately not going to lead anywhere by taking advantage of knowledge that we have initially? And it turns out we do have that kind of knowledge. We can look at just the structure of this graph so far, and we can say that right now, C's domain, for example, contains values Monday, Tuesday, and Wednesday. And based on those values, we can say that this graph is not arc consistent. Recall that arc consistency is all about making sure that for every possible value for a particular node, that there is some other value that we are able to choose. And as we can see here, Monday and Tuesday are not going to be possible values that we can choose for C. They're not going to be consistent with a node like B, for example, because B is equal to Tuesday, which means that C cannot be Tuesday. And because A is equal to Monday, C also cannot be Monday. So using that information, by making C arc consistent with A and B, we could remove Monday and Tuesday from C's domain and just leave C with Wednesday, for example. And if we continued to try and enforce arc consistency, we'd see there are some other conclusions we can draw as well. We see that B's only option is Tuesday and C's only option is Wednesday. And so if we want to make E arc consistent, well, E can't be Tuesday, because that wouldn't be arc consistent with B. And E can't be Wednesday, because that wouldn't be arc consistent with C. So we can go ahead and say E and just set that equal to Monday, for example. And then we can begin to do this process again and again, that in order to make D arc consistent with B and E, then D would have to be Wednesday. That's the only possible option. And likewise, we can make the same judgments for F and G as well. And it turns out that without having to do any additional search, just by enforcing arc consistency, we were able to actually figure out what the assignment of all the variables should be without needing to backtrack at all. And the way we did that is by interleaving this search process and the inference step, by this step of trying to enforce arc consistency. And the algorithm to do this is often called just the maintaining arc consistency algorithm, which just enforces arc consistency every time we make a new assignment of a value to an existing variable. So sometimes we can enforce arc consistency using that AC3 algorithm at the very beginning of the problem, before we even begin searching, in order to limit the domain of the variables in order to make it easier to search. But we can also take advantage of the interleaving of enforcing arc consistency with search, such that every time in the search process we make a new assignment, we go ahead and enforce arc consistency as well to make sure that we're just eliminating possible values from domains whenever possible. And how do we do this? Well, this is really equivalent to just every time we make a new assignment to a variable x, we'll go ahead and call our AC3 algorithm, this algorithm that enforces arc consistency on a constraint satisfaction problem. And we go ahead and call that, starting it with a queue, not of all of the arcs, which we did originally, but just of all of the arcs that we want to make arc consistent with x, this thing that we have just made an assignment to. So all arcs yx, where y is a neighbor of x, something that shares a constraint with x, for example. And by maintaining arc consistency in the backtracking search process, we can ultimately make our search process a little bit more efficient. And so this is the revised version of this backtrack function. Same as before, the changes here are highlighted in yellow. Every time we add a new variable equals value to our assignment, we'll go ahead and run this inference procedure, which might do a number of different things. But one thing it could do is call the maintaining arc consistency algorithm to make sure we're able to enforce arc consistency on the problem. And we might be able to draw new inferences as a result of that process, get new guarantees of this variable needs to be equal to that value, for example. That might happen one time. It might happen many times. And so long as those inferences are not a failure, as long as they don't lead to a situation where there's no possible way to make forward progress, well, then we can go ahead and add those inferences, those new knowledge, that new pieces of knowledge I know about what variables should be assigned to what values. I can add those to the assignment in order to more quickly make forward progress by taking advantage of information that I can just deduce, information I know based on the rest of the structure of the constraint satisfaction problem. And the only other change I'll need to make now is if it turns out this value doesn't work, well then down here I'll go ahead and need to remove not only variable equals value, but also any of those inferences that I made, remove that from the assignment as well. And so here then, we're often able to solve the problem by backtracking less than we might originally have needed to, just by taking advantage of the fact that every time we make a new assignment of one variable to one value, that might reduce the domains of other variables as well. And we can use that information to begin to more quickly draw conclusions in order to try and solve the problem more efficiently as well. And it turns out there are other heuristics we can use to try and improve the efficiency of our search process as well. And it really boils down to a couple of these functions that I've talked about, but we haven't really talked about how they're working. And one of them is this function here, select unassigned variable, where we're selecting some variable in the constraint satisfaction problem that has not yet been assigned. So far, I've sort of just been selecting variables randomly, just like picking one variable and one unassigned variable in order to decide, all right, this is the variable that we're going to assign next, and then going from there. But it turns out that by being a little bit intelligent, by following certain heuristics, we might be able to make the search process much more efficient just by choosing very carefully which variable we should explore next. So some of those heuristics include the minimum remaining values, or MRV heuristic, which generally says that if I have a choice between which variable I should select the variable with the smallest domain, the variable that has the fewest number of remaining values left. With the idea being, if there are only 2 remaining values left, well, I may as well prune one of them very quickly in order to get to the other, because one of those 2 has got to be the solution if a solution does exist. Sometimes minimum remaining values might not give a conclusive result if all the nodes have the same number of remaining values, for example. And in that case, another heuristic that can be helpful to look at is the degree heuristic. The degree of a node is the number of nodes that are attached to that node, the number of nodes that are constrained by that particular node. And if you imagine which variable should I choose? Should I choose a variable that has a high degree that is connected to a lot of different things? Or a variable with a low degree that is not connected to a lot of different things? Well, it can often make sense to choose the variable that has the highest degree, that is connected to the most other nodes, as the thing you would search first. Why is that the case? Well, it's because by choosing a variable with a high degree, that is immediately going to constrain the rest of the variables more, and it's more likely to be able to eliminate large sections of the state space that you don't need to search through at all. So what could this actually look like? Let's go back to this search problem here. In this particular case, I've made an assignment here, I've made an assignment here, and the question is, what should I look at next? And according to the minimum remaining values heuristic, what I should choose is the variable that has the fewest remaining possible values. And in this case, that's this node here, node C, that only has one variable left in this domain, which in this case is Wednesday, which is a very reasonable choice of a next assignment to make, because I know it's the only option, for example. I know that the only possible option for C is Wednesday, so I may as well make that assignment and then potentially explore the rest of the space after that. But meanwhile, at the very start of the problem, when I didn't have any knowledge of what nodes should have what values yet, I still had to pick what node should be the first one that I try and assign a value to. And I arbitrarily just chose the one at the top, node A, originally. But we can be more intelligent about that. We can look at this particular graph. All of them have domains of the same size, domain of size 3. So minimum remaining values doesn't really help us there. But we might notice that node E has the highest degree. It is connected to the most things. And so perhaps it makes sense to begin our search, rather than starting at node A at the very top, start with the node with the highest degree. Start by searching from node E, because from there, that's going to much more easily allow us to enforce the constraints that are nearby, eliminating large portions of the search space that I might not need to search through. And in fact, by starting with E, we can immediately then assign other variables. And following that, we can actually assign the rest of the variables without needing to do any backtracking at all, even if I'm not using this inference procedure. Just by starting with a node that has a high degree, that is going to very quickly restrict the possible values that other nodes can take on. So that then is how we can go about selecting an unassigned variable in a particular order. Rather than randomly picking a variable, if we're a little bit intelligent about how we choose it, we can make our search process much, much more efficient by making sure we don't have to search through portions of the search space that ultimately aren't going to matter. The other variable we haven't really talked about, the other function here, is this domain values function. This domain values function that takes a variable and gives me back a sequence of all of the values inside of that variable's domain. The naive way to approach it is what we did before, which is just go in order. Go Monday, then Tuesday, then Wednesday. But the problem is that going in that order might not be the most efficient order to search in. That sometimes it might be more efficient to choose values that are likely to be solutions first, and then go to other values. Now, how do you assess whether a value is likelier to lead to a solution or less likely to lead to a solution? Well, one thing you can take a look at is how many constraints get added, how many things get removed from domains as you make this new assignment of a variable to this particular value. And the heuristic we can use here is the least constraining value heuristic, which is the idea that we should return variables in order based on the number of choices that are ruled out for neighboring values. And I want to start with the least constraining value, the value that rules out the fewest possible options. And the idea there is that if all I care about doing is finding a solution, if I start with a value that rules out a lot of other choices, I'm ruling out a lot of possibilities that maybe is going to make it less likely that this particular choice leads to a solution. Whereas on the other hand, if I have a variable and I start by choosing a value that doesn't rule out very much, well, then I still have a lot of space where there might be a solution that I could ultimately find. And this might seem a little bit counterintuitive and a little bit at odds with what we were talking about before, where I said when you're picking a variable, you should pick the variable that is going to have the fewest possible values remaining. But here I want to pick the value for the variable that is the least constraining. But the general idea is that when I am picking a variable, I would like to prune large portions of the search space by just choosing a variable that is going to allow me to quickly eliminate possible options. Whereas here, within a particular variable, as I'm considering values that that variable could take on, I would like to just find a solution. And so what I want to do is ultimately choose a value that still leaves open the possibility of me finding a solution to be as likely as possible. By not ruling out many options, I leave open the possibility that I can still find a solution without needing to go back later and backtrack. So an example of that might be in this particular situation here, if I'm trying to choose a variable for a value for node C here, that C is equal to either Tuesday or Wednesday. We know it can't be Monday because it conflicts with this domain here, where we already know that A is Monday. So C must be Tuesday or Wednesday. And the question is, should I try Tuesday first or should I try Wednesday first? And if I try Tuesday, what gets ruled out? Well, one option gets ruled out here. A second option gets ruled out here. And a third option gets ruled out here. So choosing Tuesday would rule out 3 possible options. And what about choosing Wednesday? Well, choosing Wednesday would rule out one option here, and it would rule out one option there. And so I have 2 choices. I can choose Tuesday that rules out 3 options, or Wednesday that rules out 2 options. And according to the least constraining value heuristic, what I should probably do is go ahead and choose Wednesday, the one that rules out the fewest number of possible options, leaving open as many chances as possible for me to eventually find a solution inside of this state space. And ultimately, if you continue this process, we will find a solution, an assignment of variables to values that allows us to give each of these exams, each of these classes, an exam date that doesn't conflict with anyone that happens to be enrolled in 2 classes at the same time. So the big takeaway now with all of this is that there are a number of different ways we can formulate a problem. The ways we've looked at today are we can formulate a problem as a local search problem, a problem where we're looking at a current node and moving to a neighbor based on whether that neighbor is better or worse than the current node that we are looking at. We looked at formulating problems as linear programs, where just by putting things in terms of equations and constraints, we're able to solve problems a little bit more efficiently. And we saw formulating a problem as a constraint satisfaction problem, creating this graph of all of the constraints that connect 2 variables that have some constraint between them, and using that information to be able to figure out what the solution should be. And so the takeaway of all of this now is that if we have some problem in artificial intelligence that we would like to use AI to be able to solve, whether that's trying to figure out where hospitals should be, or trying to solve the traveling salesman problem, trying to optimize productions and costs and whatnot, or trying to figure out how to satisfy certain constraints, whether that's in a Sudoku puzzle, or whether that's in trying to figure out how to schedule exams for a university, or any number of a wide variety of types of problems, if we can formulate that problem as one of these sorts of problems, then we can use these known algorithms, these algorithms for enforcing arc consistency and backtracking search, these hill climbing and simulated annealing algorithms, these simplex algorithms and interior point algorithms that can be used to solve linear programs, that we can use those techniques to begin to solve a whole wide variety of problems, all in this world of optimization inside of artificial intelligence. This was an introduction to artificial intelligence with Python for today. We will see you next time.